Picture this. You're standing outside just before sunrise, the world still wrapped in that gentle blue-grey light that belongs neither to night nor to day. The stars are fading one by one, surrendering to the coming dawn. But there, low on the eastern horizon, one light refuses to yield. It hangs there like a diamond suspended against the brightening sky, so brilliant that for a moment you wonder if it might be an aircraft, a satellite, something human-made and close. But no, it's steady, patient, beautiful beyond measure. You're looking at Venus, the morning star, Earth's nearest planetary neighbour, and the brightest jewel in our sky after the sun and moon themselves. There's something almost hypnotic about Venus at dawn. Ancient peoples called it the bringer of light, watching it herald the sun's arrival with such dependable grace that they wove it into their calendars, their myths, their understanding of time itself. To see Venus in the pre-dawn sky is to witness something that human eyes have admired for thousands upon thousands of years, the same light that guided Babylonian astronomers, inspired Greek poets, and marked the seasons for Mayan priests. Hello, and welcome to the Sleepy Astronomer. Tonight, we're embarking on a journey to the most beautiful, most mysterious, and most profoundly misunderstood world in our solar system. A planet so close we could reach it in months with current technology, yet so alien that it makes the frozen moons of Jupiter seem almost welcoming by comparison. A world named for the goddess of love that turned out to be the closest thing to hell that nature has managed to create in our cosmic neighbourhood. If you're settling in for the first time, welcome aboard our gentle drift through the cosmos. And if you've travelled with me before to explore Mars's rusty deserts or Mercury's sun-scorched plains, it's wonderful to have you back among the stars. Whether you're tucked into bed, curled up in a favourite chair, or perhaps lying back where you can glimpse that same twilight sky where Venus occasionally makes her appearance, I'm so grateful you're here. Our journey tonight is one of revelations and reversals, of beauty masking horror, of the greatest cosmic disappointment in the history of planetary science. For thousands of years, Venus tantalized humanity with its brilliance. It was the evening star that lingered after sunset, the morning star that announced the dawn. Ancient astronomers tracked its movements with such precision that they could predict its appearances years in advance, even though they had no idea what they were actually looking at. When telescopes finally turned toward Venus in the 1600s, they revealed almost nothing. Unlike Mars with its polar caps and dark markings, unlike Jupiter with its colourful bands and great red spot, Venus showed observers only a featureless, cream-coloured disk that grew and shrank through phases like the Moon, but revealed nothing of its surface, nothing of its character, nothing of its secrets. The planet wore a veil of clouds so complete, so impenetrable, that it kept its true nature hidden for another 3 centuries. And what fantasies those clouds inspired. If Venus hid its face so thoroughly, surely it must have something worth hiding, something wonderful perhaps. Science fiction writers of the early 20th century imagined tropical paradises beneath those clouds, steaming jungles where dinosaurs might still roam, warm oceans teeming with exotic life. After all, Venus orbits closer to the Sun than Earth does. Surely it would be warmer, wetter, a younger Earth still in its primordial phase. The clouds only added to the romance. They had to be water vapour, didn't they? Rain clouds, perhaps, constantly replenishing those imagined oceans. Even serious scientists entertained such possibilities well into the 1950s. Venus became the planet of infinite possibility, a world where imagination could run wild because actual knowledge was so frustratingly scarce. The veil was so beautiful, so tantalizingly opaque, that it seemed cruel that we couldn't peer through it. And then we did. And what we found? Well, let's just say that sometimes the universe has a rather dark sense of humour. Venus, it turns out, is not a paradise. It's not even close to a paradise. In fact, it's difficult to imagine a more hostile environment for life as we know it anywhere in the solar system. The surface temperature hovers around 464 degrees Celsius. That's 867 degrees Fahrenheit. Hot enough to melt lead, zinc, and tin. The atmospheric pressure at the surface is 92 times greater than Earth's, equivalent to being nearly a kilometre underwater. And those beautiful clouds that inspired so many romantic visions. They're made of concentrated sulfuric acid. This is the great irony of Venus. The most beautiful planet in our sky turned out to be the most hellish world we've yet encountered. Named for the goddess of love and beauty, it proved to be a cautionary tale about the dangers of runaway greenhouse effects, a laboratory for studying how planets die, and possibly, just possibly, our own planet's future if we're not careful. But here's what makes Venus endlessly fascinating despite, or perhaps because of, its hostility. It shouldn't be this way. Venus and Earth are nearly twins in size, mass, and composition. We formed from the same cosmic material in neighbouring regions of the solar system under nearly identical conditions. Earth got oceans, life, and a climate that has remained stable enough for billions of years for complexity to evolve. Venus got sulfuric acid clouds, crushing pressures and temperatures that would vaporize a human being in moments. What went wrong? Or perhaps more unsettlingly, what went right on Earth that didn't happen on Venus? These aren't just academic questions. Understanding Venus's climate catastrophe helps us understand the delicate balance that keeps Earth habitable. Venus is our warning, our teacher, our reminder that planetary environments can fail catastrophically and permanently. From its role as the evening and morning star in ancient skies, to the Soviet probes that survived just long enough to send back images of its rocky hellscape, from radar mapping that revealed volcanic landscapes on a planetary scale to the recent controversial detection of possible signs of life floating in those acid clouds, Venus continues to surprise us, challenge us, and teach us profound lessons about how worlds work. Tonight, we'll trace Venus's journey from divine inspiration to scientific revelation. We'll explore why ancient peoples across every continent noticed this brilliant wanderer and wove it into their myths and calendars. We'll follow the centuries of telescopic frustration, trying to see through clouds that refuse to yield their secrets. We'll experience the triumph and tragedy of the Soviet Venera missions. Triumph because they succeeded beyond all reasonable expectation. Tragedy because of what they revealed. We'll understand how radar finally pierced the veil to map a world of volcanoes and rift valleys, and we'll contemplate the deepest mystery of all. Could life, perhaps life utterly unlike anything on Earth, still exist in those acidic clouds, floating in a temperate zone halfway between the surface hell and the cold of space? But we'll take our time, we'll let the story unfold gently, the way Venus itself reveals its secrets, slowly, reluctantly, in fragments and glimpses that only gradually assemble into understanding, because Venus deserves patience. This is a world that waited billions of years for visitors from Earth, that has been humanity's companion in the sky since before we were human, that has more to teach us about planetary evolution, climate science, and the nature of habitability than almost any other world we know. So settle in, get comfortable, and let's begin our gentle journey to the veiled world, not outward to the distant cold reaches of the solar system this time, but inward, closer to the sun, to our nearest planetary neighbour. There, wrapped in clouds of acid and mystery, Venus waits, patient, deadly, beautiful, and utterly unique, ready to share the secret she has kept hidden for so long. Take a deep breath, and let's lift the veil together. Have you ever noticed how certain things in nature seem to appear twice? As if the universe enjoys presenting us with pairs that are really the same thing in different guises? The ancient Greeks certainly noticed this about Venus. They looked at the brilliant star that appeared in the eastern sky before sunrise and gave it a name, Phosphorus, meaning light-bearer. Then months later, when a different brilliant star began appearing in the western sky after sunset, they named that one Hesperus, the evening star. Two separate celestial objects, they thought, each taking turns to grace the sky with unusual brightness. It's rather charming, really, this mistake. Here were some of the most careful observers in the ancient world, people who track the movements of stars and planets with remarkable precision, and they were completely fooled by Venus's game of cosmic hide-and-seek. The confusion is understandable, though. Unlike the other wandering stars, the planets that ancient astronomers distinguished from the fixed stars, Venus never ventures very far from the sun in our sky. It appears for a few months in the morning, disappears for a while, then reappears in the evening. The gap between these appearances was long enough that connecting them as the same object required careful record-keeping over months and years. Eventually someone, and we're not entirely sure who deserves the credit, though Pythagoras often gets it, realized that Phosphorus and Hesperus were the same celestial body, making its appearance on alternate sides of the sun in a regular, predictable cycle. This was one of those small but profound discoveries that shifts how we see the cosmos. One object, not two. A single wanderer playing dual roles in the sky's endless drama. But what a performance Venus puts on. At its brightest, Venus reaches an apparent magnitude of -4.7, which sounds like astronomical jargon until you realize what it means in practical terms. Venus can be so bright that it casts shadows on moonless nights. So bright that if you know exactly where to look, you can spot it in broad daylight, a tiny point of white against the blue sky. Ancient Chinese astronomers called it Tai Bai, the Great White, and recorded instances of seeing it during the day, observations that European astronomers wouldn't confirm for centuries. The brightness varies, though, in ways that puzzled astronomers for a very long time. Venus doesn't maintain a constant brilliance like some steadily burning celestial lamp. Instead, it goes through a cycle, appearing first as a modest evening star, growing brighter week by week until it dominates the twilight sky, then gradually dimming again before vanishing into the sun's glare. A few weeks pass, and then it reappears in the morning sky, going through the same brightening and dimming cycle before disappearing once more. This cycle takes 584 days to complete, which the ancient Maya tracked with such precision that they created detailed Venus tables in their codices, those beautiful, complex documents that survived the Spanish conquest. The Maya didn't just track Venus for astronomical curiosity. They used these cycles to time warfare, to schedule ceremonies, to mark the passage of longer periods than the solar year could provide. Venus became a cosmic calendar, reliable and predictable despite its seemingly wandering nature. The Maya associated Venus with their god, Kukulkan, the feathered serpent, and they paid particular attention to something they call the heliacal rising, the moment when Venus first becomes visible in the dawn sky after its period of invisibility. This was considered a dangerous time, an inauspicious moment when the gods were watching. Military campaigns would wait for the proper Venus cycle. Kings would time their coronations to avoid unfavorable Venus positions. The planet wasn't just a light in the sky, it was a force that influenced human affairs. But they weren't alone in this. Across the ocean in ancient Babylon, astronomers were conducting their own meticulous observations of Venus. The Babylonians identified Venus with Ishtar, their goddess of love and war. Note that combination. And they tracked the planet's movements on clay tablets with such accuracy that modern astronomers still consult these ancient records. The Babylonians noticed something the Greeks had missed. Venus's movements were so regular, so mathematically precise, that they could be predicted years in advance. Here's where it gets interesting from a purely observational standpoint. Venus can stray at most about 47 degrees from the Sun as seen from Earth. That's the result of its orbit being smaller than Earth's, keeping it always relatively close to our star in the sky. This maximum separation, what astronomers call the greatest elongation, is when Venus appears brightest and most impressive. At these moments, Venus is showing us a particular phase, like the Moon does, though this wouldn't be discovered until Galileo turned his telescope toward the planet in 1610. Those phases were revolutionary. When Galileo observed Venus through his primitive telescope, barely powerful enough to reveal Jupiter's largest moons, he saw something that shouldn't exist according to the prevailing Earth-centered model of the universe. Venus went through a complete set of phases, from a thin crescent to nearly full, just like the Moon. But in the old Ptolemaic system, where everything supposedly circled Earth, Venus should only ever show crescent phases. The full phases proved that Venus must orbit the Sun, not Earth. This was dangerous knowledge in 1610. Galileo had to be careful about how he presented it, encoding his discovery in an anagram before announcing it openly. The phases of Venus were one of the key pieces of evidence that eventually convinced the scientific community that Earth was not the center of everything, that we orbited the Sun along with the other planets, a rather humbling revelation, courtesy of the goddess of love. But even Galileo's telescope couldn't penetrate Venus's clouds. He saw the phases, the changing illumination as Venus orbited the Sun, but the surface remained stubbornly invisible. Larger telescopes, better optics, more careful observations over the next few centuries, none of it helped. Venus showed a blank, cream-coloured face to even the most powerful telescopes of the 19th century. Mars revealed its polar caps and dark markings. Jupiter displayed colourful bands and the great red spot. Saturn showed off its magnificent rings. Venus showed nothing but an impenetrable veil. This only deepened the planet's mystery and, if anything, enhanced its mythological associations. Here was a world that refused to be fully known, that kept its secrets behind clouds no telescope could pierce. The connection to Venus as a goddess, to the idea of beauty, mystery, and hidden depths, seemed almost poetic. Ancient peoples who named the planet had somehow intuited something about its character, even if they had the details spectacularly wrong. Let's talk about those names for a moment, because nearly every culture that looked up at the night sky and tracked celestial movements gave Venus special attention. The Romans called it Venus after their goddess of love and beauty, borrowed from the Greek Aphrodite. But the associations went deeper than simple appearance. Venus the goddess was known for her dual nature. She could be gentle and nurturing, or fierce and demanding. She was beauty, yes, but also passion, desire, sometimes even conflict. The Aztecs knew Venus as Tlahuizcalpantecutli when it appeared as the morning star, a name that roughly translates to Lord of the Dawn, but associated it closely with Quetzalcoatl, the feathered serpent god. Like the Maya, they tracked Venus cycles with precision and considered the morning star appearance particularly significant. The planet's heliacal rising was thought to bring harmful influences, and priests would perform rituals to protect people from Venus's metaphorical arrows. In Hindu astronomy, Venus is Shukra, the guru of the demons in ancient texts, but also considered the brightest and most auspicious of the celestial teachers. The name means bright or clear, and Venus is associated with beauty, love, and the arts, themes that recur across cultures in ways that seem almost suspiciously consistent. Ancient Egyptians, characteristically thorough in their astronomical observations, actually had multiple names for Venus, depending on whether it was in the morning or evening sky, appeared in the morning or evening sky. As the morning star, it was Tiumutiri. As the evening star, Uwaiti. Like the Greeks, they initially thought they were observing two different objects, though Egyptian astronomers eventually figured out the truth, probably through their own careful record-keeping over generations. The Islamic astronomer of the medieval period called Venus al-Zuhara, and their observations of the planet were extraordinarily detailed. They measured its movements with precision that wouldn't be matched in Europe for centuries, and their work eventually made its way to European scholars during the Renaissance, helping to fuel the astronomical revolution. Even in Japan, where Venus is called Yoiboshi when it appears as the evening star, the planet found its way into poetry and art. Haiku masters referenced Venus's appearance at twilight as a symbol of transience and beauty, that moment when daylight fades and the evening star emerges, steady and brilliant despite the changing light around it. What's fascinating is how all these cultures, separated by vast distances and different mythological frameworks, associated Venus with similar concepts: beauty, love, desire, and often a hint of danger or duality. The Babylonian Ishtar was both love and war. The Greek Aphrodite could be tender or terrible depending on her mood. The Aztec morning star brought harmful influences even as it heralded the dawn. There's something about Venus's behavior in the sky, its brightness, its regular but complex cycle of appearances and disappearances, its dual role as both morning and evening star, that seems to have inspired similar symbolic interpretations across human cultures. Of course, we now know that these mythological associations tell us more about human psychology than about the actual planet. Venus isn't governed by divine whims or astrological influences. It's a physical world following the mathematical laws of orbital mechanics, its appearances and disappearances determined by geometry and gravity, not by the moods of gods. But here's something worth considering. Those ancient observers were incredibly skilled at what they did. Without telescopes, without photography, without any of our modern instruments, they tracked Venus's movements with such precision that the Maya could predict its cycle 584 days in advance, that the Babylonians could calculate its greatest elongations, that astronomers in China could spot it in daylight. They were wrong about what Venus was. They didn't know it was a world like Earth, wrapped in clouds, suffering under conditions that would vaporize a human being. But they weren't wrong about its importance. Venus teaches us something about planetary motion because its orbit is so clearly visible from Earth. As an inferior planet, meaning it orbits closer to the Sun than we do, Venus demonstrates principles that apply to all planetary orbits. The way it swings from one side of the Sun to the other, never straying too far from our star in the sky, illustrates the geometry of the solar system, in a way that's observable with nothing but patient attention and clear skies. Ancient astronomers didn't know they were observing a world with a surface hot enough to melt lead, where sulfuric acid rain falls from the clouds but evaporates before reaching the ground, where the atmospheric pressure would crush a human like a tin can. They saw beauty, mystery, a wandering light that played peekaboo with the sun. And in a way, they weren't entirely wrong. Venus is mysterious. It is beautiful, at least from a distance. And it does play games with observers, hiding its true nature behind that eternal veil of clouds. The transition from mythological Venus to scientific Venus, from goddess to geological catastrophe, took thousands of years and involved some of the greatest minds in human history. Each culture added its piece to the puzzle. The Maya with their precise cycles, the Babylonians with their mathematical predictions, the Greeks with their realization that the morning and evening stars were one, Galileo with his phases proving Venus orbited the sun, and eventually, in our own era, the spacecraft that would finally pierce the veil and reveal the hell beneath the beauty. But before any of that could happen, humanity had to learn to see Venus not as a divine presence, but as a place, a world with its own character, its own story, its own terrible beauty. The ancient astronomers who tracked Venus across the sky, who wove it into their myths and calendars, who associated it with their gods of love and war. They were taking the first steps in a journey that would ultimately lead to Soviet probes melting on Venus's surface, to radar mapping revealing volcanic landscapes, to the realization that our beautiful sister planet was actually our dire warning. All of that started with people looking up at twilight, noticing that brilliant point of light, and caring enough to track where it went, when it appeared, how it moved through the stars. Science often begins with wonder, and Venus has inspired wonder for as long as humans have had eyes to see and minds to question. The goddess of love, as it turns out, had secrets far stranger than any myth could capture. If you were to line up Venus and Earth side by side in some cosmic photograph, you'd be forgiven for thinking you were looking at twins. Venus measures 12,104 kilometers in diameter, just 650 kilometers shy of Earth's 12,742 kilometers. That's about 95% of Earth's size, close enough that if Earth were a basketball, Venus would be, well, a very slightly smaller basketball. Not exactly the dramatic size difference you might expect between planets. The similarities continue when you look at mass. Venus contains about 82% of Earth's mass, and its density is nearly identical to ours, 5.24 grams per cubic centimetre, compared to Earth's 5.52. This tells us something important. Venus is made of the same stuff we are. Rocky material, iron core, silicate mantle. The basic construction is essentially identical. Stand on Venus's surface. If you could somehow survive the experience, and you'd feel gravity pulling at you with about 90% the force you experience on Earth. You'd be slightly lighter, slightly bouncier, but not dramatically so. Not like the Moon's 1/6 gravity or Mars's 1/3. This is what makes Venus so fascinating and so frustrating at the same time. We have a near twin right next door, formed from the same cosmic materials at roughly the same time, in neighbouring orbits around the same star. By all rights, Venus should be Earth's sister in more than just size. We should be looking at two blue worlds with oceans and continents, two planets where water cycles between ocean and sky, two potential cradles for life. Instead, we got Earth, temperate, wet, teeming with life in every conceivable niche from deep ocean trenches to high mountain peaks. And we got Venus, a planet-sized pressure cooker where the surface temperature hovers at 464 degrees Celsius. That's 867 degrees Fahrenheit if you prefer, though honestly at those temperatures, the choice of scale feels academic. This is hot enough to melt lead, zinc and tin. Hot enough that if you could somehow stand on Venus's surface, protected from the pressure and acid, you would watch metal puddle and flow like water. The pressure is perhaps even more immediately deadly than the temperature. At Venus's surface, the atmospheric pressure reaches 92 bars, 92 times Earth's sea level pressure. To experience equivalent pressure on Earth, you'd need to dive nearly a kilometre beneath the ocean's surface, down where sunlight can barely penetrate and the water presses in with crushing force. Submarines that explore these depths need thick hulls of reinforced steel to prevent being crumpled like tin cans. Now imagine trying to stand in that pressure while also being heated to temperatures that would melt metal. The phrase, hell on Earth, doesn't quite capture it, because hell, as traditionally imagined, is still located on Earth with Earth-like conditions compared to Venus. Venus is hell taken to an entirely different level, hell designed by a malevolent physicist with access to advanced thermodynamics and a complete disregard for anyone's comfort. And yet, the cruelest trick Venus plays is that it almost certainly didn't start this way. The current scientific consensus suggests that early Venus, young Venus, billions of years ago, when the solar system was still finding its rhythm, might have been far more hospitable. It might have had oceans. It might have had a climate not entirely unlike Earth's. For perhaps as long as 2 billion years, Venus could have been the paradise that early science fiction writers imagined when they looked at those impenetrable clouds and dreamed of tropical worlds. What happened? That's the question that keeps planetary scientists awake at night, sometimes literally. How does a world go from potentially habitable to categorically hellish? The answer lies in a process so insidious, so self-reinforcing, that once it starts, it becomes almost impossible to stop: the runaway greenhouse effect. You're probably familiar with the basic greenhouse effect. It's what keeps Earth comfortably warm instead of frozen solid. Our atmosphere contains gases like carbon dioxide and water vapor that are transparent to visible light, but opaque to infrared radiation. Sunlight passes through, warms the surface, and when that warmth tries to radiate back into space as infrared heat, the greenhouse gases trap some of it, keeping our planet's surface temperature higher than it would be otherwise. This is good. This is what makes Earth habitable. Without any greenhouse effect, Earth's average temperature would be about minus 18 degrees Celsius instead of the pleasant plus 15 degrees we actually enjoy. But there's such a thing as too much of a good thing. Add more greenhouse gases to the atmosphere and you trap more heat, and the temperature rises. Rising temperature causes more water to evaporate from the oceans. Water vapor is itself a greenhouse gas, so now you have even more greenhouse gases, which trap even more heat, which causes even more water to evaporate. You can see where this is going. On Earth, we have several mechanisms that prevent this feedback loop from spiraling out of control. Our oceans absorb enormous amounts of carbon dioxide. Rainfall washes CO2 out of the atmosphere. Rock weathering, the chemical reaction between atmospheric CO2 and silicate rocks, locks carbon away in carbonate minerals. These processes create a kind of planetary thermostat, keeping Earth's temperature within bounds even when things fluctuate. Venus, it appears, lost its thermostat. Perhaps the planet was slightly closer to the Sun, receiving slightly more solar energy. Perhaps volcanic activity released massive amounts of CO2 all at once. Perhaps some combination of factors. Venus's lack of a magnetic field, its slow rotation, its particular atmospheric chemistry, created the perfect storm for climate catastrophe. Whatever triggered it, once the runaway greenhouse began, it was unstoppable. Temperatures climbed, water evaporated. More water vapor meant more heat trapping. Eventually, Venus's oceans boiled away completely. The water vapor high in the atmosphere was broken apart by solar ultraviolet radiation, photodissociation in technical terms, splitting H2O into hydrogen and oxygen. The lightweight hydrogen escaped to space. Some oxygen may have combined with surface rocks, rusting the planet from the inside out, but most of it was probably lost to space as well, stripped away by the solar wind because Venus lacks a strong magnetic field to protect its upper atmosphere. With the water gone, there was nothing to regulate the carbon dioxide. Volcanic eruptions continued adding CO2 to the atmosphere. Venus shows evidence of extensive volcanic activity throughout its history, but with no oceans to dissolve it, no rain to wash it away, no weathering cycle to lock it in rocks. The CO2 just accumulated, and accumulated, and accumulated. Today, Venus's atmosphere is 96.5% carbon dioxide. For comparison, Earth's atmosphere is about 0.04% CO2, and we're worried about the effects of increasing that to 0.05%. Venus's atmosphere is literally thousands of times more concentrated in greenhouse gases than ours, and the result is a surface temperature that doesn't vary much between day and night, between equator and poles, between seasons, because Venus doesn't really have seasons given its nearly upright axial tilt. The entire planet is uniformly, consistently, thoroughly baked. The remaining 3.5% of Venus's atmosphere is mostly nitrogen, with trace amounts of sulfur dioxide, argon, water vapor, carbon monoxide, helium, and neon. That sulfur dioxide is particularly notable because it's what forms those beautiful, terrible clouds that hide Venus's surface from view. High in the atmosphere, where temperatures are cooler, sulfur dioxide combines with water vapor to create sulfuric acid. Not dilute sulfuric acid like you might encounter in a chemistry lab, with proper safety equipment. Concentrated sulfuric acid, the kind that would dissolve organic matter on contact, that would eat through most materials given time. These sulfuric acid clouds form in 3 distinct layers between 50 and 70 kilometers above Venus's surface. They're remarkably efficient at reflecting sunlight. Venus's high albedo, its brightness as seen from Earth, comes from these reflective clouds. About 75% of the sunlight that hits Venus bounces back into space, never reaching the surface. And yet, despite this, Venus is still the hottest planet in the solar system. Even Mercury, which orbits much closer to the Sun and receives far more solar energy, doesn't get as hot as Venus, because Mercury has virtually no atmosphere to trap heat. The clouds also create weather patterns that are utterly alien to anything we experience on Earth. High above the surface, where the clouds form, winds race around the entire planet at speeds of about 120 meters per second. That's roughly 270 miles per hour, faster than the strongest hurricanes on Earth. These winds complete a circuit of Venus in just 4 days, even though the solid planet beneath takes 243 Earth days to complete one rotation. This super rotation of the atmosphere is one of the great unsolved mysteries of Venus meteorology. We don't fully understand what drives winds to move 60 times faster than the surface rotates beneath them. The acid rain that falls from these clouds never reaches the surface. The temperature increases so dramatically as you descend through Venus's atmosphere that by the time the acid droplets fall to about 25 kilometers altitude, they've evaporated, turning back into sulfur dioxide and water vapor that rise back up to the cloud layer to begin the cycle again. It's a closed loop, an endless rain that never quite completes its journey, another small impossibility in Venus's catalogue of extremes. Despite having virtually no water in its atmosphere today, less than 0.003%, Venus once had enough water to cover its surface with an ocean perhaps 80 meters deep. That's not as deep as Earth's oceans, which average about 3.7 kilometers, but it's substantial. All of that water is gone now, lost to space over billions of years of photodissociation and atmospheric escape. What remains is a planet that has been thoroughly, completely dehydrated. The lack of a magnetic field has proven crucial to Venus's fate. Earth's magnetic field, generated by the churning of our molten iron core, creates a protective bubble, the magnetosphere, that deflects the solar wind away from our upper atmosphere. Venus has no such protection. The solar wind, a constant stream of charged particles flowing from the sun, slams directly into Venus's upper atmosphere, stripping away lighter molecules and preventing the planet from holding on to whatever water vapor remains. We're not entirely sure why Venus lacks a magnetic field. It has an iron core similar to Earth's, but generating a magnetic field requires more than just molten metal. You need convection currents, you need the right kind of rotation, you need a delicate balance of thermal and rotational energy. Venus's slow rotation might be part of the problem. A planet that takes 243 days to spin once simply doesn't have the rotational energy to drive the kind of dynamo effect that generates strong magnetic fields. Then there's Venus's peculiar rotation, which we'll explore in more detail later, but deserves mention here. Venus rotates backwards relative to most planets. While Earth and most other planets spin counterclockwise when viewed from above their north poles, Venus spins clockwise. This retrograde rotation, combined with the planet's extraordinarily slow spin rate, means that a day on Venus, one complete rotation, is actually longer than a Venusian year. The planet completes an orbit around the Sun in 224.7 Earth days, but takes 243 Earth days to rotate once. This creates an interesting quirk. If you could somehow stand on Venus's surface and watch the Sun move across the sky, which you couldn't because the clouds completely obscure any view of the Sun, you would see it rise in the west and set in the east, the opposite of what we see on Earth. And the interval between one sunrise and the next, a solar day, what we normally think of as a day, would be about 117 Earth days. Imagine waiting 4 months between one sunrise and the next. The combination of all these factors, the thick CO2 atmosphere, the lack of magnetic field, the slow retrograde rotation, the loss of all surface water, has created a world that is in almost every measurable way hostile to life as we understand it. And yet, this is the world that formed right next door to Earth, from the same materials, at the same time, under seemingly similar conditions. The question that haunts planetary scientists is not really what went wrong on Venus, but rather what went right on Earth. Because when you look at the physics involved, when you understand how easily a runaway greenhouse can begin, and how impossible it is to stop once started, Earth's continued habitability starts to seem like a rather fortunate accident. We're the right distance from the Sun, yes. We have plate tectonics to recycle carbon, yes. We have a large moon that stabilized our rotation and climate, yes. We have a magnetic field to protect our atmosphere, yes. But Venus had its own advantages, it had its own opportunities, and somehow, somewhere along the way, things diverged. Venus and Earth, twins in size and composition, went down radically different evolutionary paths. One became a haven for life, for complexity, for consciousness capable of wondering about its celestial neighbour. The other became a lesson in planetary climatology, a warning about the fragility of habitable conditions, a demonstration that worlds can die not with a bang, but with an accumulation of small catastrophes that eventually snowball into permanent desolation. In a strange way, studying Venus is like looking at Earth's ghost, not what Earth will definitely become, but what it could become under the wrong circumstances. It's a reminder that planetary habitability isn't guaranteed, isn't permanent, isn't robust against all possible changes. Venus stands as evidence that the universe doesn't particularly care about maintaining comfortable conditions for life. And yet, despite all of this, despite the heat, the pressure, the acid clouds, the complete absence of liquid water, there are scientists who wonder if Venus might still harbour life. Not on the surface, certainly, but perhaps floating in those clouds in the narrow altitude range where temperatures and pressures are surprisingly Earth-like. But that's a story for later, when we've learned more about Venus's atmosphere and its continuing capacity to surprise us. For now, it's enough to understand that Venus, beautiful, bright Venus, the goddess of love in the evening sky, is hiding beneath those clouds a world so fundamentally hostile that it makes the vacuum of space seem welcoming by comparison. The twin that went wrong, the sister planet that took a different path, the cautionary tale hanging right there in our sky, bright enough to cast shadows, close enough that we might visit it someday if we're clever enough and brave enough. Close enough to be a constant reminder, there but for grace go we. There's something almost maddening about Venus's clouds when you really think about them. Imagine trying to study a neighbour's house when they've installed curtains so thick, so impenetrable, that you can't see even a hint of what's inside. You can measure the curtains themselves, their colour, their thickness, how they move in the breeze, but the rooms beyond remain perpetually hidden. Now, imagine those curtains are made of concentrated sulfuric acid, and you're beginning to appreciate the challenge that Venus presented to astronomers for over 3 centuries. When Galileo first turned his telescope toward Venus in 1610, he saw a bright, featureless disk that changed shape as it went through its phases, but revealed absolutely nothing about its surface. Better telescopes in the 1700s and 1800s showed the same featureless disk. By the early 1900s, astronomers had telescopes powerful enough to see individual craters on the Moon, to map the polar caps of Mars, to observe the cloud bands of Jupiter in exquisite detail. Venus? Still a blank, cream-coloured sphere. The clouds aren't just opaque, they're maddeningly, comprehensively, thoroughly opaque across the entire visible spectrum. They reflect about 75% of the sunlight that hits them, which is why Venus appears so bright in our sky. But they also prevent us from seeing even the faintest hint of surface features below. It's as if Venus is actively refusing to be known, hiding behind a veil that turned out to be far more hostile than anyone imagined. Those clouds form in 3 distinct layers between about 50 and 70 kilometers above Venus's surface, roughly where Earth's stratosphere meets the mesosphere, though the comparison is imperfect because Venus's atmosphere is structured so differently from ours. The upper cloud deck, at around 65 to 70 kilometers, consists of tiny droplets of sulfuric acid, maybe a micron or so in diameter, about 1/100th the width of a human hair. These droplets are suspended in the thin upper atmosphere, creating a haze that stretches completely around the planet. Below this, at about 55 to 65 kilometers, lies the middle cloud layer where the acid droplets grow larger and more concentrated. This is the thickest, most opaque part of the veil, the main curtain, if you will. The acid concentration here reaches about 85%, which is about as concentrated as you can get while still having liquid droplets. For reference, the sulfuric acid used in car batteries is typically around 30 to 50% concentration. What we're talking about here would make industrial chemists nervous. The lower cloud deck from roughly 50 to 55 kilometers is somewhat thinner and more variable. The droplets here are larger still, and beneath this lowest cloud layer, there's a region of haze that extends down to about 30 kilometers before you finally reach the relatively clear lower atmosphere. Though clear is a relative term when you're talking about an atmosphere so thick and hot that it would crush and cook you simultaneously. Here's what makes these clouds particularly fascinating from a chemical standpoint. Sulfuric acid doesn't just appear spontaneously. You need sulfur dioxide, which Venus has in abundance, likely from volcanic activity, and you need water vapor, which Venus has in trace amounts. High in the atmosphere, where temperatures are cooler, around -10 to 20 degrees Celsius, the SO2 reacts with water and oxygen to form sulfuric acid through a series of chemical reactions that wouldn't be out of place in an industrial chemistry textbook. The acid droplets form, grow larger through condensation, and eventually become heavy enough to fall. As they descend into the warmer lower atmosphere, they evaporate again, breaking back down into sulfur dioxide and water vapor, which then rise back up to the cloud layer to repeat the cycle. It's a closed loop, a conveyor belt of acid that has been running for millions or billions of years, creating rain that never reaches the ground. This is rather different from Earth's water cycle, where rain falls, reaches the surface, flows into oceans and rivers, evaporates and returns to the sky. On Venus, the cycle completes itself entirely in the atmosphere, never touching the surface below. It's a ghost rain, eternally falling and never landing. The clouds also contain other compounds mixed in with the sulfuric acid, particles of elemental sulfur that give the clouds a yellowish tint, traces of iron chloride that might account for some of the ultraviolet absorption we observe, and various other exotic chemicals that we're still trying to fully catalogue. Venus's atmosphere is a chemist's nightmare, and dream rolled into one, nightmarish because of the harsh conditions, but fascinating because of the complex chemistry occurring in those clouds. But perhaps the most bizarre aspect of Venus's atmosphere isn't the clouds themselves, but how they move. Remember how we mentioned that Venus rotates once every 243 Earth days? That's a leisurely, almost glacial rotation by planetary standards. You'd expect the atmosphere to rotate at roughly the same speed, following the solid planet beneath it, the way Earth's atmosphere roughly follows Earth's rotation. Instead, the upper atmosphere of Venus races around the entire planet in just 4 days. 4 days. This superrotation, wind speeds reaching about 120 meters per second at the cloud tops, means the atmosphere is moving about 60 times faster than the surface beneath it. It's as if Earth's atmosphere decided to lap the planet every 5 or 6 hours, regardless of how fast the ground was turning. This shouldn't happen. It violates our basic intuitions about how atmospheres should behave. And yet, there it is, confirmed by observation after observation. Spacecraft watching the cloud patterns, tracking individual features as they whip around the planet, have verified these extraordinary wind speeds. The mechanism driving this superrotation is still not completely understood, though scientists have several theories involving the way solar heating interacts with the planet's slow rotation and the unique thermal properties of Venus's thick atmosphere. The wind patterns create features in the clouds that are visible in ultraviolet light, even though they're invisible in normal optical wavelengths. There's a distinctive Y-shaped pattern near Venus's equator that appears and disappears over periods of days or weeks, created by the atmospheric circulation. Near the poles, the clouds form strange vortex patterns, swirling structures that look almost like hurricanes, but are driven by entirely different physics than Earth storms. These polar vortices are particularly strange. Imagine looking down at either pole and seeing the clouds spiral inward in a complex double vortex structure that looks almost like a flower with petals made of acid clouds. The structure shifts and changes over timescales of hours to days, driven by the poleward flow of the super-rotating atmosphere. It's beautiful in images, in a cold, alien sort of way, the kind of beauty you might admire from a very safe distance. The super-rotation isn't uniform across all altitudes either. As you descend through Venus's atmosphere, the winds gradually slow down. At the surface, wind speeds are only about 1 meter per second, roughly 2 miles per hour, a gentle breeze by Earth standards. But in that thick, dense atmosphere, even slow winds can exert significant force. It's the difference between a gentle breeze in air and the same speed current in water. The denser fluid carries more momentum. Lightning is another atmospheric mystery on Venus. Earth has spectacular lightning storms driven by water droplets and ice particles colliding in thunderclouds, creating charge separation and eventual electrical discharge. Venus doesn't have water clouds, but it appears to have lightning nonetheless. Lots of it, in fact. The mechanism is different, probably involving sulfuric acid droplets instead of water, but the result is the same. Electrical discharges crackling through the clouds. Some observations suggest Venus might experience nearly constant lightning activity, with hundreds of lightning strikes per second across the planet. Though this is still debated, detecting lightning from orbit is tricky, and distinguishing actual lightning from other electromagnetic phenomena in Venus's complex ionosphere isn't straightforward. But if the higher estimates are correct, Venus might be the lightning capital of the solar system, a world where acid clouds are constantly illuminated by electrical storms. The chemistry happening in those clouds is extraordinarily complex and not yet fully understood. Sulfuric acid is the dominant component, yes, but the clouds also contain unknown ultraviolet absorbers, compounds that soak up UV light, but whose exact identity remains mysterious despite decades of study. When you look at Venus in ultraviolet wavelengths, you see dark patches in the clouds, regions where something is absorbing UV radiation. But what? Various candidates have been proposed: elemental sulfur, iron chloride, sulfur dioxide, even organic compounds. Each has some evidence supporting it. Each has problems explaining all the observations. It's possible, likely even, that multiple compounds contribute to the UV absorption, creating a complex cocktail of chemicals that varies with altitude, latitude, and time. This is where Venus's veil becomes not just a barrier to seeing the surface, but an active area of research in its own right. The clouds aren't just an obstacle, they're a phenomenon, a massive atmospheric chemistry experiment that's been running for eons, producing conditions that don't exist anywhere else in the solar system. There's also the question of what happens at the boundary between cloud layers, where different temperature and pressure regimes create complex mixing dynamics. Turbulence, convection currents, chemical reactions occurring at different rates at different altitudes. It all combines to create an atmosphere in constant motion, constantly changing, never quite the same from one moment to the next, despite the overall stability of the cloud layers. For early observers, before we understood any of this chemistry, the clouds represented pure mystery. The veil metaphor comes naturally to humans. We have centuries of literature and mythology about veils hiding truth, beauty obscured by coverings, knowledge concealed behind barriers that must be penetrated to reveal what lies beneath. Medieval alchemists spoke of removing veils to access hidden knowledge. Ancient mystery religions used literal veils in their ceremonies to separate the initiated from the uninitiated. Venus's clouds fit perfectly into this archetypal framework. Here was the goddess of love and beauty, hiding her face from prying eyes, revealing nothing despite humanity's best efforts to see through her disguise. The romantic imagination seized on this. What wonderful secrets might those clouds conceal? What paradise might exist in the hidden world below? Science fiction writers of the early 20th century, working with the limited data available, imagined Venus as a world of perpetual clouds because it was wetter than Earth, warmer because it was closer to the sun, perhaps a younger Earth still in its steamy primordial phase. Edgar Rice Burroughs, who gave us the Mars of John Carter, also wrote about Venus. His version featured primitive humans, prehistoric beasts, and jungle adventures beneath those eternal clouds. It was a planetary romance in the literary sense, a setting for adventure and discovery. The reality, as we've seen, turned out to be somewhat less adventurous and considerably more deadly. But the metaphor of the veil persists because it captures something essential about Venus. This is a world that doesn't give up its secrets easily, that maintains mystery even after centuries of study, that still surprises us with new discoveries, despite having been observed since ancient times. Even now, with all our modern technology, we can't see Venus's surface in ordinary light. We need radar to penetrate the clouds, infrared sensors to peer through atmospheric windows at specific wavelengths, where the thick air becomes relatively transparent. And even then, we're getting indirect information, reconstructed images, data that needs interpretation rather than the direct visual observation that makes Mars and the Moon feel so immediate and accessible. There's something almost willful about it, as if Venus has decided that if it can't be the paradise early scientists hoped for, it will at least maintain some dignity by refusing to be easily known. The veil stays up, and we have to work for every scrap of information we extract from this shrouded world. The atmospheric windows, those specific infrared wavelengths where Venus's atmosphere becomes somewhat transparent, are themselves fascinating. Around 1 micron wavelength, thermal emission from the hot surface can escape through the clouds, allowing us to map temperature variations. Around 2.3 microns, we can sometimes glimpse the surface itself in a ruddy glow, seeing elevation features as variations in brightness because higher terrain is cooler and emits less thermal radiation. But these windows are narrow, both in wavelength and in the conditions required to use them effectively. You need the right instruments, the right atmospheric conditions, the right viewing geometry. It's not like looking at Mars through a telescope where you can see surface features clearly on any night with good seeing conditions. Venus makes you work for every glimpse, every measurement, every new piece of data. And yet scientists keep trying, keep observing, keep sending probes and orbiters to study this veiled world. Because beneath that frustrating, impenetrable, acid-soaked cloud layer lies a planet, a real physical world with geology, maybe even current volcanic activity, possibly active tectonics of some kind. A world that was Earth's twin in formation, but took a radically different path in evolution. A world that might teach us crucial lessons about climate, about atmospheric chemistry, about the factors that determine whether a planet remains habitable or descends into permanent inhospitality. The veil is part of Venus's identity now. It's not just hiding the surface, it's an essential part of what makes Venus Venusian. Those clouds regulate the planet's temperature, create its bizarre, super-rotating winds, possibly harbour the only potentially habitable zone on the entire planet. and continue to puzzle scientists with their complex chemistry and mysterious UV absorbers. In a strange way, we've come to appreciate the veil itself rather than just seeing it as an obstacle to studying what lies beneath. Venus's atmosphere is an exotic, extreme environment in its own right, a laboratory for studying chemistry and physics under conditions that don't exist on Earth. The fact that it also happens to completely obscure the surface is almost secondary to the intrinsic fascination of those racing acid clouds, that super-rotating wind system, that eternal rain that never lands. The perpetual veil of Venus, frustrating, fascinating, deadly beautiful, remains one of the planet's defining features, even as we learn more about what lies beneath. Even as radar mapping reveals the surface in exquisite detail, the clouds maintain their mystery, their chemistry incompletely understood, their dynamics not fully explained, their secrets still partially concealed. Venus keeps some cards close to her chest even now. The goddess of love, it seems, knows the value of maintaining a little mystery. If planets were students in some cosmic classroom, Venus would be the one sitting in the back row, facing the wrong direction, doing everything opposite to what the teacher expects, and somehow still managing to show up for class. Because Venus doesn't just rotate slowly, it rotates backwards. And not just backwards, but so slowly that its day is longer than its year. It's the kind of behaviour that would get a planet sent to the principal's office if such things existed in orbital mechanics. Let's start with the basics, because Venus's rotation is strange enough that it deserves a careful explanation. Most planets in our solar system spin in the same direction they orbit, counterclockwise when viewed from above the solar system's north pole. This is what we call prograde rotation, and it makes intuitive sense because planets formed from a rotating disk of material around the young sun. That disk was spinning in one direction, so naturally most of the objects that formed from it maintained that same rotational direction. Earth spins prograde, completing one rotation in about 24 hours. Mars spins prograde, taking about 24.6 hours. Jupiter, Saturn, Uranus, which is tilted on its side but still technically rotating prograde relative to its own north pole, Neptune, all spinning counterclockwise, all following the expected pattern. And then there's Venus, spinning clockwise. This retrograde rotation means that if you could stand on Venus's cloud tops, which you can't, but let's pretend, you would see the sun rise in the west and set in the east. Everything would be backwards compared to what we experience on Earth. The stars would wheel across the sky in the opposite direction. If Venus had a moon, it would appear to orbit backwards compared to the planet's rotation. But wait, it gets stranger. Venus takes 243 Earth days to complete one full rotation on its axis. That's longer than any other planet in the solar system. For comparison, Jupiter, a planet so large you could fit over 1,300 Earths inside it, spins once in less than 10 hours. Jupiter is enormous, and yet it whips around like a cosmic top. Venus is roughly Earth-sized and takes 243 days to lazily complete a single turn. Now, Venus orbits the Sun once every 224.7 Earth days, so Venus completes an entire orbit, a full year, before it finishes a single rotation. Read that again, because it's genuinely strange. Venus's year is shorter than its day. If you were somehow living on Venus's surface, you would celebrate a birthday before experiencing one complete sunrise to sunrise cycle. Except it's even more complicated than that, because of how rotation and orbital motion interact. A solar day, the time from one noon to the next noon, or one sunrise to the next sunrise, depends on both the planet's rotation and its orbital motion. When you factor in Venus's retrograde rotation and its orbital period, you get a solar day on Venus that lasts about 117 Earth days. So, from one sunrise to the next sunrise, about 117 Earth days would pass, during which Venus would have completed roughly half an orbit around the Sun. This means that if you could somehow plant yourself on Venus's surface and mark time by the Sun's position in the sky, again, impossible because of the clouds, but bear with me, you would experience 2 complete day-night cycles in the time it takes Venus to go around the Sun once. The Sun would rise in the west, slowly arc across the sky over about 58.5 Earth days, set in the east, and then you'd have another 58.5 Earth days of night before the Sun rose in the west again. The mathematics of this gets wonderfully weird. Venus rotates 243 times, in the time it takes to complete 224.7 orbits. Wait, no, that's backwards. Let me try again. In the time Venus completes one rotation, 243 Earth days, it completes slightly more than one orbit, 224.7 Earth days. This means, you know what? There's a reason why planetary motion gave ancient astronomers headaches. The point is, everything about Venus's rotation is backwards and slow and peculiar. So what happened? How does a planet end up rotating the wrong way at the wrong speed? This is one of those questions that keeps planetary scientists debating over coffee at conferences, because we don't have a definitive answer, just several plausible theories. The most popular theory involves a giant impact sometime in Venus's early history. Picture the young solar system as a cosmic billiards table, with planet-sized objects careening around, occasionally smashing into each other. We know Earth experienced at least one massive collision, the impact that created our moon, and it's reasonable to think Venus might have suffered something similar. If a large enough object hit Venus at just the right angle, it could have imparted enough angular momentum to flip the planet's rotation. Think of it like hitting a spinning top from the side. If you hit it hard enough, you can reverse its spin. Scale that up to planetary sizes and you have a mechanism for retrograde rotation. The impact would need to be significant. Perhaps an object the size of Mercury or Mars slamming into Venus billions of years ago. But the early solar system was chaotic enough that such collisions were not uncommon. The problem with this theory is that such an impact should have left evidence. A large moon created from the debris, perhaps, or an asymmetric distribution of mass in Venus's interior, or chemical signatures in the planet's composition. We don't see strong evidence for any of these. Venus has no moon at all. Its interior appears relatively symmetric, and its composition is what we'd expect for a planet that formed where it did without major disruption. So maybe the impact hypothesis isn't quite right, or maybe the evidence has been erased by billions of years of geological activity. Venus shows signs of having resurfaced itself relatively recently in geological terms, perhaps 300 to 500 million years ago, when massive volcanic activity may have covered over older features. If Venus experienced a giant impact early in its history, and then completely resurfaced itself 500 million years ago, any evidence of that ancient collision might be gone. Another theory involves atmospheric tides raised by the Sun. Earth experiences ocean tides from the Moon's gravity, but you can also have atmospheric tides from solar heating. On Venus, with its incredibly thick atmosphere, solar tides could be significant. Over billions of years, the friction between atmospheric tides and the solid planet could gradually slow the rotation, potentially even reversing it. Computer models suggest this might work, but it requires very specific conditions. The atmosphere needs to be thick enough to exert significant tidal forces. The planet's rotation needs to start in a particular range of speeds, and the whole process needs billions of years to operate. Venus meets these criteria, but the models are sensitive to assumptions and initial conditions. It's plausible, but not proven. There's also the question of Venus's axial tilt, which adds another layer of strangeness to the rotation story. Earth is tilted about 23.5 degrees relative to its orbital plane, which gives us our seasons. Mars is tilted about 25 degrees. Jupiter is only tilted about 3 degrees. These tilts likely resulted from the chaotic collisions and gravitational interactions of the early solar system. Venus, though, is tilted about 177 degrees. Think about that for a moment. If a planet is tilted 180 degrees, it's completely upside down. Its north pole is pointing south and its south pole is pointing north. Venus is tilted 177 degrees, which is almost but not quite upside down. Technically, you could describe this as either a 177-degree tilt with retrograde rotation or a 3-degree tilt with prograde rotation if you just flip which pole you call north. Astronomers have chosen to describe it as retrograde rotation with a 177-degree tilt, which makes Venus unusual on 2 counts rather than 1. Whether you think of Venus as spinning backwards or as nearly upside down is somewhat a matter of convention, but either way, something significant happened to Venus's rotation at some point in its history. The near-perfect tilt, so close to 180 degrees, is actually suspicious in its precision. Random collisions would be more likely to produce random tilts. The fact that Venus ended up so close to being exactly upside down suggests that maybe the atmospheric tidal theory has merit, because those tidal forces would naturally drive the planet toward either 0 degrees, perfectly upright, or 180 degrees, perfectly upside down, depending on initial conditions. Or perhaps Venus experienced multiple giant impacts that effectively randomized its rotation, and the current state is just where it happened to end up after all the chaos settled down. Multiple impacts could also explain why Venus has no large moon. If debris from impacts was repeatedly scattered and reaccreted, you might not end up with a stable satellite. There's also a fascinating quirk related to how Venus's rotation interacts with Earth. Venus and Earth are locked in what's called a near resonance. When Venus and Earth come to their closest approach, an event called inferior conjunction, when Venus passes between Earth and the Sun, Venus almost always shows the same face to Earth. It's not a perfect resonance like the Moon always showing the same face to Earth, but it's close enough to be statistically interesting. This happens because Venus's solar day of 117 Earth days is almost exactly 1/5 of the synodic period between Earth and Venus, the time it takes for the 2 planets to return to the same relative positions. 5 Venus solar days equals about 585 Earth days, while the synodic period is about 584 days. Close enough that over multiple conjunctions, Venus tends to present the same hemisphere toward Earth. Is this coincidence? Probably, but it's a remarkable one. Some scientists have suggested that tidal forces from Earth might have influenced Venus's rotation enough to create this near resonance, but the forces involved seem too small to have such a dramatic effect. It's more likely just a quirk of orbital mechanics. The universe occasionally produces patterns that look meaningful, but are really just coincidence. The slow rotation has other effects beyond just making for absurdly long days and nights. For one thing, it's probably why Venus lacks a magnetic field. Earth's magnetic field is generated by the motion of molten iron in our planet's core, a geodynamo driven partly by Earth's rotation. Venus has an iron core similar to Earth's, but its glacially slow rotation means there's not enough rotational energy to drive the same kind of dynamo effect. Without a magnetic field, Venus's atmosphere is directly exposed to the solar wind, that stream of charged particles flowing from the Sun. This has contributed to the loss of Venus's water over billions of years as the solar wind strips away hydrogen from the upper atmosphere. It's one more way that Venus's strange rotation has contributed to making the planet the hellscape it is today. The slow rotation also affects atmospheric circulation. On Earth, our relatively fast rotation creates the Coriolis effect, which influences weather patterns and ocean currents. Venus's slow rotation means a much weaker Coriolis effect, which is part of why the super-rotating atmosphere can exist. With weak Coriolis forces, there's less to prevent the upper atmosphere from racing around the planet independent of the surface rotation. In ancient mythology and astrology, retrograde motion was always significant. When planets appeared to move backwards against the background stars, a result of Earth overtaking them in our respective orbits, it was considered ominous, a disruption of the natural order. The fact that Venus itself actually does rotate backwards seems almost appropriate given its mythological associations. The goddess of love and beauty, the most brilliant object in the sky after the sun and moon, the planet that fooled astronomers into thinking it was two different objects. Of course, it would spin the wrong way. Of course, it would be the contrarian of the planetary family. Modern science fiction has occasionally played with the weirdness of Venus's rotation. Stories set on Venus sometimes feature the concept of walking with the Terminator, staying in the narrow twilight zone between the scorching day side and the frigid night side by walking westward at just the right speed. With a solar day lasting 117 Earth days, you'd only need to walk about 6 kilometers per hour to keep pace with the Terminator. Impractical for many reasons, the crushing pressure, the heat, the lack of solid ground in many places, but a fascinating thought experiment. The backwards rotation also means that if you could somehow watch Venus from space over long periods, you'd see the planet's features moving opposite to what you'd expect. The clouds race around from east to west, following the super-rotation, while the planet itself slowly turns beneath them from west to east. Its motion within motion, layers of rotation at different speeds and in different directions, a cosmic reminder that planets don't all follow the same rules. There's something almost rebellious about Venus's rotation, as if the planet decided early on that if it couldn't be the paradise world that science fiction writers imagined, it would at least be interesting. The slowest rotation, the backward spin, the nearly upside-down tilt, Venus takes conventional planetary behavior and inverts it, creating a world that challenges our assumptions about how planets should work. And perhaps that's the real lesson of Venus's bizarre rotation. The universe doesn't particularly care about our intuitions or expectations. Planets can spin backwards. Days can be longer than years. Worlds can be nearly upside down. The solar system is full of quirks and oddities, each one a reminder that nature is far more creative than our tidy models suggest. Venus spins on, slowly, backwards, nearly upside down, taking its own sweet time to complete each rotation while racing around the sun twice. It's the planet that does everything wrong and yet remains perfectly stable in its orbit, perfectly content with its peculiar rotation, perfectly happy to be the exception to every rule. The goddess of love, spinning backwards through space, hiding her face behind acid clouds, taking 4 months between sunrises, and still somehow managing to be the brightest, most beautiful jewel in our evening sky. If that's not the most Venus thing imaginable, I don't know what is. There's something genuinely heroic about sending a machine to its death, especially when you know exactly how it will die, approximately when it will die, and can do almost nothing to prevent it. The Soviet Venera program, Venera meaning Venus in Russian, was a decades-long exercise in engineering determination, a series of missions where success was measured not in years of operation but in minutes, where every scrap of data returned was a triumph against impossible odds. Picture yourself as an engineer in the Soviet space program in the early 1960s. You've just watched your country succeed brilliantly with Sputnik and Gagarin, demonstrating clear superiority in space exploration. Now you're being asked to design a spacecraft to land on Venus. You know the planet is hot. Early radio astronomy has suggested surface temperatures in the hundreds of degrees. You know the atmosphere is thick. Spectroscopic analysis has revealed massive amounts of carbon dioxide, but the full horror of Venus's surface conditions isn't yet understood. So you design your probe. You make it sturdy, you add heat shielding, you plan for a rough entry, and you send it toward Venus, hoping for the best. Venera 1, launched in February 1961, lost contact with Earth a week into its journey, probably due to an overheated orientation sensor. It flew past Venus in May without sending back any data, becoming the first human-made object to pass near another planet, but unable to tell anyone about it. A technological ghost, forever silent, still orbiting the Sun somewhere in the inner solar system. Venera 2 and 3, launched in 1965, both failed to return data. Venera 3 actually reached Venus's atmosphere in March 1966, becoming the first spacecraft to impact another planet's surface, though impact might be generous, given that it probably disintegrated in the atmosphere on the way down. No data, no images, no confirmation of success beyond knowing it had reached the right general area of space at the right time. These early failures were frustrating but educational. Each mission taught Soviet engineers something about Venus's environment, even if that lesson was simply, our spacecraft weren't nearly tough enough. The atmosphere was thicker than expected. The temperatures were higher than predicted. The entry forces were more extreme than models suggested. Venera 4, launched in June 1967, was built tougher. It carried instruments designed to measure temperature, pressure, and atmospheric composition during descent. On October 18, 1967, it entered Venus's atmosphere and began transmitting data. For 93 minutes, as it descended slowly by parachute, Venera 4 sent back measurements that revolutionized our understanding of Venus. The atmosphere was indeed mostly carbon dioxide, about 95%, confirming earlier spectroscopic observations. The temperature increased steadily during descent, reaching levels that exceeded the probe's measurement capabilities. And the pressure kept climbing, far beyond what engineers had anticipated. Venera 4's transmissions ceased at an altitude of about 25 kilometers above the surface. Engineers initially thought it had reached the ground, but later analysis revealed the horrible truth. The spacecraft had been crushed by atmospheric pressure long before reaching the surface. The atmosphere was so much denser than predicted that Venera 4 simply couldn't survive the descent. Its mission ended in the middle atmosphere, squeezed into oblivion by the weight of all that carbon dioxide. This was both devastating and valuable. Devastating because the probe failed to reach its intended destination. Valuable because now Soviet engineers knew just how extreme the conditions truly were. Venus wasn't just hot and thick-aired. It was a pressure chamber that would crush submarines, a furnace that would melt lead, an environment so hostile that surviving there even briefly would require complete redesign of every system. Venera 5 and 6, launched in 1969, were built even stronger, with reinforced pressure vessels and heat shields designed for more extreme conditions. Both entered Venus's atmosphere in May 1969. Both returned data during descent, Both were crushed by atmospheric pressure before reaching the surface, Venera 5 at about 24 kilometers altitude, Venera 6 at about 10 kilometers. But the data they returned was extraordinary. Temperature measurements showed the surface had to be around 475 degrees Celsius. Pressure measurements indicated surface pressure might reach 90 or even 100 Earth atmospheres. Chemical analysis revealed trace amounts of nitrogen, water vapor, and other compounds mixed with the overwhelming carbon dioxide. With each failure, Soviet engineers learned. With each crushed probe, the specifications for the next mission became more extreme. The pressure vessels needed to be stronger, not submarine strong, but more like deep ocean submersible strong, capable of withstanding pressures equivalent to being a kilometer underwater. The cooling systems needed to be more efficient, able to dissipate heat in an environment where the outside temperature exceeded anything encountered on Earth's surface. And so, in August 1970, the Soviets launched Venera 7. This probe was built like a titanium tank. The pressure sphere was made of specially hardened materials. The cooling system used circulating fluid to keep internal components below their failure temperatures for as long as possible. The parachute was designed to slow descent in Venus's thick atmosphere, buying time for data transmission. On December 15, 1970, Venera 7 entered Venus's atmosphere. It descended slowly through the acid clouds, through the increasingly hot and dense lower atmosphere. Its instruments measured and transmitted, even as the external temperature climbed past 400 degrees, past 450 degrees, approaching 500 degrees Celsius. And then it landed. Hard, probably. Analysis suggests the parachute failed during descent, and Venera 7 free fell the last kilometer or so, hitting the surface at about 17 meters per second. But it survived the impact, and for 23 minutes it transmitted data from the surface of Venus. 23 minutes. Not long by any measure, but long enough to confirm what those earlier missions had suggested. Venus's surface temperature was around 475 degrees Celsius. Surface pressure was approximately 90 atmospheres. The probe was sitting on actual solid ground beneath all that atmosphere. For the first time in history, humanity had received transmissions from the surface of another planet. The signal was weak and distorted. Later analysis would extract additional data from the recording, extending the mission duration to about 50 minutes total. But in those initial 23 minutes, Venera 7 became the first successful landing on another planet, the first human-made object to touch another world's surface and tell us about it. The Soviets weren't done. Venera 8, launched in 1972, carried improved instruments and a redesigned cooling system. It landed successfully in July 1972 and operated for 50 minutes on the surface, returning data about light levels. Yes, enough sunlight penetrates the clouds for surface photography to be possible, and chemical composition of the soil. But the real triumph came with Venera 9 and 10 in 1975. These weren't just landers, they were orbiters as well, with each mission consisting of 2 spacecraft. The orbiter would study Venus from space while the lander descended to the surface, and most ambitiously, the landers carried cameras. After centuries of wondering what Venus's surface looked like beneath those clouds, after decades of failed missions and crushed probes, the Soviets were finally going to take photographs. Venera 9 landed on October 22, 1975 on the slope of a volcanic highland. It operated for 53 minutes before the heat finally killed it. But in those 53 minutes, it transmitted the first photograph ever taken from the surface of another planet. The image showed rocks, sharp rocks, fractured and angular, lying scattered across a relatively flat surface. The rocks showed little erosion despite their age. No wind or water had worn them smooth. The sky was bright enough that shadows were visible. It was an alien landscape, but recognizably geological. Not so different from rocky terrain on Earth, except for the orange-brown lighting and the knowledge that the air was hot enough to melt lead and thick enough to crush steel. Venera 10 landed 3 days later in a different region and returned similar images. Flat volcanic plains covered with rocks that looked like weathered basalt. The rocks were flatter and smoother than those at the Venera 9 site, suggesting different geological processes or different ages of formation. These images changed everything. Venus's surface wasn't mysterious anymore. It was real, visible, documented. The goddess had finally lifted her veil, at least partially, and what lay beneath was neither paradise nor completely alien. It was geology, planetary science in action, a world of rocks and stones and ancient lava flows. Venera 11 and 12, launched in 1978, carried improved instruments and operated for about 95 minutes each on the surface. They detected possible lightning in Venus's atmosphere and measured electrical activity in the clouds. Venera 11 also carried a drill to sample the soil, though it failed to operate properly in the extreme heat. Then came Venera 13 and 14 in 1982, and these were the crown jewels of the program. Both carried color cameras. Both had improved cooling systems that extended surface operations to over 2 hours. Both successfully analyzed soil samples with X-ray fluorescent spectrometers. Venera 13 landed on March 1, 1982, and operated for 127 minutes, more than 2 hours in an environment that would vaporize a human being in seconds. It returned the first color images from Venus's surface, showing that strange orange-brown lighting that results from sunlight filtering through the thick atmosphere and acid clouds. The images showed flat terrain covered with rocks and what looked like weathered volcanic material. More importantly, Venera 13 successfully drilled into the surface and analyzed the soil composition. The results indicated basaltic rock similar to volcanic material on Earth, evidence that Venus's geology, while operating under very different conditions, follows similar basic principles to our own planets. Venera 14, landing 3 days later, operated for 57 minutes and returned similar data from a different location. The soil analysis showed variations in composition between the two sites, suggesting different volcanic sources or different ages of eruption. Venera 15 and 16, launched in 1983, didn't attempt to land but instead carried radar mapping equipment. They spent months in orbit mapping Venus's northern hemisphere, revealing large-scale geological features invisible through the clouds. These missions bridged the gap between the surface photographs from the landers and the comprehensive global mapping that would come later with NASA's Magellan mission. The Venera program represents something remarkable in the history of space exploration: persistence in the face of brutal, unforgiving conditions. Each failure taught something valuable. Each success pushed the boundaries of what seemed possible. Soviet engineers designed spacecraft to survive in an environment more hostile than anywhere on Earth, and they succeeded. There's also something poignant about the Venera landers still sitting on Venus's surface, silent now, their electronics long since failed from heat and corrosion. They're monuments to human curiosity, to the drive to explore, even when exploration seems impossible, to the willingness to send machines into hell just to learn what hell looks like. The program wasn't perfect. Some missions failed completely. Some returned partial data. The photographs were black and white initially, and even the color images had limitations. The cameras couldn't operate long enough to take many shots. The lighting was dim and strange, and the thick atmosphere created distortion. But between 1961 and 1984, the Soviet Union launched 16 missions to Venus, and while many failed, the successes fundamentally changed our understanding of our sister planet. They proved you could survive Venus's surface, at least briefly. They showed what that surface looked like. They measured the temperature, pressure, and composition with precision. They demonstrated that Venus, for all its hostility, was still a planet, still bound by the same physics and chemistry that govern Earth, just operating under far more extreme conditions. In the Cold War context, Venus became the Soviet Union's planet in a way that Mars or the Moon never were. While Americans focused on lunar landings and Mars orbiters, the Soviets mastered Venus, sending probe after probe to that hellish surface, each one a small triumph of engineering over entropy. The engineering challenges were extraordinary. Imagine trying to build electronics that can function at temperatures hot enough to melt common metals. Imagine designing a cooling system that must dissipate heat in an environment where the outside temperature is hundreds of degrees higher than your coolant. Imagine creating a camera that can take photographs when it's literally sitting inside what amounts to an oven set to incinerate. And then imagine doing all of this knowing that your spacecraft will only survive for an hour or two at most, that every component is on borrowed time from the moment of landing, that no repair is possible and no second chances exist. The Venera engineers worked under constraints that would seem impossible today, with 1960s and 70s technology that had to be not just functional, but extraordinarily robust. The success rate improved over time as engineers learned from each mission. The early Veneras were shots in the dark, educated guesses about what might work. By the time of Venera 13 and 14, the Soviets had refined their designs to the point where they could reliably land on Venus, operate for 2 hours or more, take photographs, and analyze soil samples. That progression from ignorance to mastery over 2 decades represents some of the finest engineering work of the space age. There's been nothing like it since. After the Venera program, Venus has received relatively little attention from landers. Atmospheric probes, yes. Orbiters with radar mapping, certainly. But no spacecraft has touched down on Venus's surface since the Soviet missions of the 1980s. The environment is simply too hostile, the scientific return too limited compared to the enormous engineering effort required, and the resources of spacefaring nations have focused elsewhere. But those Soviet probes still sit there on the rocky plains and volcanic highlands of Venus, slowly deteriorating under the relentless heat and pressure. They were the first human-made objects to reach another planet's surface and survive long enough to tell us about it. They sent back the first photographs from another world. They proved that human ingenuity could triumph, even briefly, over one of the most hostile environments in the solar system. The Venera program was Venus exploration's golden age, unlikely to be repeated anytime soon. And in those grainy, orange-tinted photographs of Venus's rocky surface, in those 127 minutes of Venera 13's survival against impossible odds, in the entire arc of missions from Venera 1's silent failure to Venera 16's successful radar mapping, we see something quintessentially human: the refusal to accept that any question is truly unanswerable, any destination truly unreachable. Venus may be hell, but the Soviets went there anyway, and they came back with pictures. If you've ever used a flashlight to find something in a dark room, you understand the basic principle of radar. Send out a signal, wait for it to bounce back, and use the reflection to figure out what's out there. Scale that up to planetary dimensions, Replace visible light with radio waves and add some extraordinarily sophisticated mathematics, and you have the tool that finally allowed us to see Venus's surface in comprehensive detail. The Venera missions had given us glimpses, small circular photographs showing rocks and terrain immediately around the landing sites. But these were like looking at Earth's surface through a handful of portholes scattered randomly across the planet. You might see a beach, a forest, a desert, but you'd have no idea how they connected, no sense of the larger geological story. To truly understand Venus, we needed a map. The problem, as we've discussed, is that Venus's clouds are completely opaque to visible light and most other wavelengths of electromagnetic radiation. But radio waves, particularly in certain wavelength ranges, can penetrate those sulfuric acid clouds as if they weren't there. Send radio waves down through the atmosphere, wait for them to bounce off the surface, measure how long the return trip takes and at what angle the waves come back, and you can construct an image of the terrain below. This technique, called synthetic aperture radar, or SAR, had been developed for Earth observation and military reconnaissance during the Cold War. The basic idea is that you can simulate having a very large radar antenna by moving a smaller antenna along a path and combining the signals mathematically. It's rather like the way your two eyes, separated by just a few inches, can create depth perception, except radar does it by moving through space and using very precise timing. NASA's Magellan mission, launched in May 1989, carried a radar system specifically designed to map Venus's surface. The spacecraft itself was built partly from spare parts left over from other missions. Its main bus was a spare Voyager component. Its solar panels came from satellite programs. Its antenna was borrowed from another project. It was a spacecraft built on a budget, assembled from the cosmic equivalent of salvaged materials, but its radar system was state-of-the-art. Magellan arrived at Venus in August 1990 and began the patient work of mapping. The spacecraft would orbit Venus every 3.26 hours, and during each orbit it would point its antenna down at the surface and sweep the radar beam across a narrow strip of terrain as it flew overhead. Then it would turn its antenna toward Earth and spend the rest of the orbit transmitting the data back home before turning to map another strip on the next pass. Strip by strip, orbit by orbit, day by day, Magellan built up a comprehensive map of Venus's surface. The process took years. The primary mapping mission ran from 1990 to 1992, with additional cycles filling in gaps and improving resolution in certain areas. By the time Magellan finally exhausted its propellant and was deliberately sent into Venus's atmosphere to burn up in October 1994, it had mapped over 98% of Venus's surface, with resolution down to about 100 meters per pixel. What those radar maps revealed was a world far more complex and geologically interesting than anyone had expected. Venus wasn't a dead planet with an ancient cratered surface like the Moon or Mercury. It was geologically young, with a surface that appeared to have been completely resurfaced, relatively recently in planetary terms, perhaps 300 to 500 million years ago. The evidence for this resurfacing was both what Magellan saw and what it didn't see. Impact craters were relatively rare on Venus and distributed almost uniformly across the surface. On a truly ancient surface like the Moon's, you'd see vast differences in crater density, older regions heavily cratered, younger regions with fewer impacts. Venus showed none of this variation, suggesting that the entire surface had been renewed at roughly the same time. The mechanism for this global resurfacing is still debated. The leading theory involves massive volcanic activity, perhaps triggered by a catastrophic release of heat from Venus's interior. Unlike Earth, which releases heat gradually through plate tectonics and ongoing volcanic activity, Venus might store heat for hundreds of millions of years, years before experiencing a planet-wide volcanic episode that completely buries the old surface under fresh lava flows. Imagine the entire planet erupting simultaneously, or at least erupting extensively across most of its surface over a relatively brief period of perhaps tens of millions of years. Lava flows covering continents, volcanic plains extending for thousands of kilometers, the old landscape buried beneath layer after layer of molten rock that gradually cooled into the surface we see today. The volcanic features Magellan discovered were spectacular in their scale and variety. There were shield volcanoes like those in Hawaii, except some of them were enormous. Mount Mons rises about 8 kilometers above the surrounding plains, making it taller than any volcano on Earth, except for Hawaii's Mauna Kea, when measured from the ocean floor. And unlike Earth's volcanoes, which are scattered across moving tectonic plates, Venus's volcanoes had remained stationary over their hotspots, allowing them to grow to tremendous sizes. Magellan also revealed features called coronae, circular or oval structures ranging from about 100 to 1,000 kilometers across, characterized by concentric ridges and radial fractures. They look almost like frozen ripples in the planet's crust, as if something below had pushed upward, stretched the surface, and then subsided again. The leading explanation involves mantle plumes, hot blobs of material rising from deep within Venus, bulging the crust upward before cooling and sinking back down. There were pancake domes, flat, circular volcanic features that look exactly like their name suggests. These appear to be formed from extremely viscous lava that oozed out onto the surface and spread into neat circular shapes before solidifying. On Earth, such viscous lava would cool too quickly to form such perfect shapes, but Venus's high surface temperature and atmospheric pressure might allow lava to remain fluid longer. The radar images showed vast lava channels, some extending for hundreds of kilometers across the surface, evidence of incredibly fluid lava flows that carve paths through the landscape. There were also features called tesserae, regions of intensely deformed terrain with multiple overlapping sets of ridges and valleys, suggesting complex tectonic stresses that folded and fractured the crust. Two major highland regions emerged from Magellan's mapping, Ishtar Terra in the north and Aphrodite Terra near the equator. These are Venus's equivalents to continents, though they're smaller relative to the planet's size than Earth continents are. Ishtar Terra, named for the Babylonian goddess we encountered earlier, contains Maxwell Montes, Venus's highest mountain range, rising about 11 kilometers above the mean planetary radius. Maxwell Montes is named for James Clerk Maxwell, the physicist who developed the theory of electromagnetic radiation that makes radar possible. A fitting tribute given that radar is how we finally saw this mountain. It's also the only surface feature on Venus not named for a woman, having been named before the International Astronomical Union adopted the convention of using female names for Venusian geography. That naming convention deserves a moment's attention because it's both wonderful and slightly chaotic. Every feature on Venus, craters, mountains, plains, valleys, is named for a woman, real or mythological, from human history and culture. You have craters named for scientists like Marie Curie and writers like Jane Austen. You have coronae named for goddesses from every culture. Ishtar, Artemis, Quetzalcoatl, Atahensik. You have plains named for everyone from Sedna of Inuit mythology to Guinevere of Arthurian legend. The result is a planetary map that reads like a who's who of feminine achievement and mythology across human history. It's a subtle but profound shift from the pattern on other worlds, where features are named predominantly for men. Venus became a canvas for recognizing women's contributions to human culture, science, and mythology. Aphrodite Terra, the larger of the two continental regions, stretches nearly halfway around Venus's equator. It's a complex region of mountains, valleys, and fractured terrain that shows evidence of extensive tectonic activity. Unlike Earth's plate tectonics, which involves large pieces of crust moving around the surface, Venus appears to have experienced more localized deformation, crustal stretching and compression without global plate motion. This lack of plate tectonics is actually somewhat mysterious. Earth's plates are driven partly by the cooling of the interior. Hot mantle material rises at mid-ocean ridges, spreads out, cools, and sinks back down at subduction zones, dragging the plates along. Venus is roughly the same size as Earth, with presumably similar internal heat, so why no plate tectonics? One theory points to water, or rather the lack of it. On Earth, water in the crust acts as a lubricant, allowing rocks to deform and slide past each other more easily. Venus's bone-dry crust might be too stiff and strong for plate tectonics to operate. Instead, heat builds up until it's released catastrophically in those global resurfacing events we mentioned earlier. The impact craters Magellan found were also interesting for what they revealed about Venus's atmosphere. Small impactors, asteroids or comets less than a few kilometers across, would be broken up or destroyed completely by the thick atmosphere before reaching the surface. This means Venus's atmosphere acts as a shield against smaller impacts, similar to how Earth's atmosphere protects us from smaller meteorites. The craters that do exist on Venus tend to be larger, created by impactors big enough to punch through the atmosphere, and many of them are remarkably well preserved, with sharp rims and clear ejector patterns, because there's no wind or water erosion to wear them down over time. The only thing that erases craters on Venus is being buried under fresh lava flows. Magellan's radar could also measure surface roughness at centimeter scales by analyzing how the radio waves scattered. Smooth surfaces like recent lava flows reflect radar waves differently than rough, rocky terrain. This allowed scientists to identify different rock types and surface ages without ever touching the ground, a kind of remote geology performed from orbit using nothing but the way radio waves bounced off distant rocks. The mission also revealed that some of Venus's volcanoes might still be active. Certain features showed signs of being very young, fresh lava flows with no impact craters on them, suggesting they formed within the last few million years or perhaps even more recently. Some scientists have proposed that volcanic eruptions might still occur on Venus today, though we haven't yet caught one in the act. There was also evidence for what might be cryovolcanism, volcanic activity involving materials other than molten rock. Some features on Venus's surface showed characteristics consistent with eruptions of carbon dioxide or sulfur compounds rather than traditional lava. In Venus's high-pressure environment, such materials could behave like fluids and create volcanic-style features. The radar mapping also allowed scientists to create topographic maps showing Venus's elevation across the planet. Venus turned out to be remarkably flat compared to Earth. About 80% of the surface lies within a kilometer of the mean planetary radius, creating vast plains interrupted by scattered highlands and volcanic features. If Venus had oceans, which it doesn't and never will again, most of the planet would be shallow seafloor. Magellan's mission fundamentally changed our understanding of Venus from a mysterious veiled world to a geologically documented planet. We can now see the scars of ancient volcanism, trace the paths of lava flows, identify regions of crustal deformation, and begin to understand the geological processes that shaped this world. But Magellan did more than just map the surface. By the end of its mission, the spacecraft was running low on propellant, so NASA engineers decided to conduct a series of experiments using Magellan itself as a probe. They lowered its orbit until it was skimming through the outermost layers of Venus's atmosphere, measuring density and composition through the drag on the spacecraft. Finally, in October 1994, Magellan's orbit decayed completely, and the spacecraft plunged into Venus's atmosphere, burning up and likely scattering fragments across the surface it had spent 4 years mapping. It was a deliberate end, chosen to extract maximum science from the mission, and somehow fitting, Magellan had revealed Venus's surface to humanity, and in return, Venus claimed the spacecraft as a permanent resident. The data Magellan sent back fills volumes and continues to be analysed decades later. New discoveries are still being made in those radar images, new volcanic features identified, new questions raised about Venus's geological history. The mission proved that you don't need to land on a planet to understand its surface. Sometimes the right instrument in orbit can reveal as much or more than a probe on the ground. And perhaps most beautifully, Magellan demonstrated that electromagnetic radiation, the same physics that creates visible light and the warmth of sunlight, could be bent to a different purpose, allowing us to see through barriers that would defeat ordinary vision. Venus kept her surface hidden from optical telescopes for centuries, but radio waves cared nothing for sulfuric acid clouds. The goddess finally showed her face, not to our eyes, but to our mathematics, and she was more beautiful, more complex, and more geologically fascinating than anyone had imagined. If you've ever left a car parked in the sun with the windows rolled up, you've experienced a miniature version of the greenhouse effect. Sunlight streams through the glass, warming everything inside. That warmth tries to escape as infrared radiation, heat, but glass is partly opaque to infrared, so some of that heat gets trapped. The car becomes an oven, reaching temperatures far higher than the air outside. Now imagine that effect scaled up to an entire planet, with an atmosphere 92 times thicker than Earth's, and composed almost entirely of the most efficient greenhouse gas nature commonly produces. Imagine that greenhouse running not for an afternoon, but for billions of years, with no way to turn it off, no way to open the windows and let the heat out. That's Venus. The greenhouse effect itself isn't inherently catastrophic. In fact, it's essential for life on Earth. Without any greenhouse warming, our planet's average temperature would be about minus 18 degrees Celsius, well below the freezing point of water. The modest amount of carbon dioxide, water vapor, and methane in our atmosphere traps just enough heat to raise our average temperature to a pleasant 15 degrees Celsius. The greenhouse effect is what makes Earth habitable rather than a frozen snowball. But there's a tipping point, a threshold beyond which the greenhouse effect becomes self-reinforcing in ways that lead to catastrophe. This is what happened on Venus, and understanding exactly how and why it happened has become one of the most important questions in planetary science, not just for understanding Venus, but for understanding Earth's own climate future. Let's walk through the process step by step, because it's both elegant and terrifying in its inexorable logic. Start with a planet roughly Earth size and composition, orbiting closer to the Sun than we do, about 108 million kilometers, compared to Earth's 150 million. This closer orbit means Venus receives about 1.9 times as much solar energy per square meter as Earth does. Not double, but significantly more. That extra energy matters. In the early solar system, billions of years ago, the Sun was actually dimmer than it is today, a phenomenon called the faint young sun paradox. This means that young Venus might not have been dramatically hotter than young Earth despite its closer orbit. It's plausible, though still debated, that early Venus had liquid water on its surface, perhaps even oceans. But as the sun gradually brightened over hundreds of millions of years, Venus began receiving more and more energy. Temperatures slowly climbed, and here's where the feedback loop begins. As temperatures increase, more water evaporates from the oceans. Water vapor is a potent greenhouse gas. It traps infrared radiation very efficiently. More water vapor in the atmosphere means more heat trapped, which means higher temperatures, which means more evaporation. On Earth, this feedback loop is kept in check by several mechanisms. When the atmosphere holds more water vapor, you get more clouds, which reflect sunlight back into space, providing a cooling effect. You also get more rainfall, which removes water vapor from the atmosphere and returns it to the oceans. And crucially, Earth has a mechanism for removing carbon dioxide from the atmosphere over long timescales, the carbonate-silicate cycle. Here's how that cycle works. Atmospheric CO2 dissolves in rainwater, creating a weak acid. That acidic rainwater falls on silicate rocks, the kind that make up most of Earth's crust, and chemically weathers them, locking the carbon into carbonate minerals like limestone. These carbonates eventually get carried by rivers to the ocean, where they settle as sediment. Then, through plate tectonics, that sediment gets subducted into the mantle, heated, and the CO2 is released again through volcanic eruptions. It's a cycle that regulates Earth's atmospheric CO2 over millions of years, creating a kind of planetary thermostat. Venus appears to have lost its ability to run this cycle. Perhaps the planet got too hot for liquid water to exist on the surface. Without liquid water, you can't have weathering of silicate rocks. Without weathering, you can't remove CO2 from the atmosphere. And without that removal mechanism, volcanic eruptions just keep adding more and more CO2, with no way to take it back out. As Venus's temperature climbed and its oceans evaporated, the water vapor in the upper atmosphere was exposed to intense ultraviolet radiation from the sun. UV radiation can split water molecules apart, a process called photodissociation, breaking H2O into hydrogen and oxygen. The lightweight hydrogen atoms easily escape to space, especially from a planet like Venus that lacks a protective magnetic field. The oxygen either escapes as well or reacts with surface rocks, essentially rusting the planet from the inside. Over hundreds of millions of years, perhaps longer, Venus lost its water. All of it. Every ocean, every lake, every molecule of water vapor that couldn't be sequestered in the thick lower atmosphere where temperatures and pressures keep trace amounts stable. The planet was thoroughly, completely dehydrated. Meanwhile, volcanic activity, which appears to have been extensive throughout Venus's history, continued pumping CO2 into the atmosphere. With no oceans to dissolve it, no rain to wash it away, no carbonate formation to lock it in rocks, the CO2 just accumulated. The atmosphere grew thicker and thicker, trapping more and more heat, creating the hellish conditions we observe today. This runaway greenhouse is essentially irreversible. Once you've lost your water and filled your atmosphere with enough CO2, you can't go back. The planet is locked into its current state and will remain so until something truly catastrophic happens, perhaps the sun's evolution into a red giant billions of years from now, which will likely vaporize Venus entirely. Carl Sagan, who spent much of his career studying Venus's atmosphere and climate, recognized the profound implications for Earth. In the 1960s and 70s, when he was helping to interpret the first data from Venus probes, Sagan understood that Venus wasn't just an alien world to study for its own sake. It was a natural experiment in planetary climate catastrophe, a warning of what can happen when greenhouse warming spirals out of control. Sagan was one of the first scientists to connect Venus research to concerns about Earth's climate. He pointed out that while Earth is in no immediate danger of becoming another Venus, we're farther from the Sun, we have active oceans and a functioning carbon cycle. We're nonetheless engaged in a massive, uncontrolled experiment by pumping CO2 into our atmosphere at rates far faster than natural processes can remove it. The comparison between Venus and Earth has become a central part of climate science education, though it's important to be precise about the parallels and differences. Earth is not going to become Venus. We're too far from the Sun. We have too much water, and our carbon cycle is too robust. Even in the worst-case scenarios for human-caused climate change, Earth will remain habitable for humans, though potentially much less pleasant and with much greater disruption to ecosystems and human civilization. But Venus demonstrates the principle that planetary climates have tipping points, thresholds beyond which feedback loops become self-reinforcing and changes become irreversible on human timescales. It shows that planets can transition from potentially habitable to definitively uninhabitable. It proves that greenhouse atmospheres can create surface conditions hostile to life. There's also the question of timing that makes Venus's story particularly relevant to Earth's climate concerns. Venus likely lost its habitability over hundreds of millions of years, possibly longer. The transition from a potentially ocean-bearing world to the hell we see today was gradual by human standards, though catastrophically fast by geological ones. Human civilization is adding CO2 to Earth's atmosphere on timescales of decades and centuries, not millions of years. We're conducting a rapid-fire experiment in atmospheric composition that has no real parallel in Earth's natural history, except during mass extinction events. Venus reminds us that atmospheres matter, that composition determines climate, and that once you push a planetary system past certain thresholds, returning to the previous state becomes difficult or impossible. The scientific study of Venus has directly informed Earth climate modelling in practical ways. The physics of how CO2 traps heat is the same on both planets. Venus just has far more of it operating under extreme conditions. Understanding Venus's atmospheric circulation, its cloud chemistry, its heat distribution, helps us validate the models we use to predict Earth's climate future. Venus also provides a test case for understanding how atmospheres respond to extreme greenhouse forcing. The fact that Venus's temperature is nearly uniform across the planet, day and night, equator and poles, demonstrates how effectively a thick CO2 atmosphere can redistribute heat. This validates theoretical predictions about greenhouse warming and gives us confidence in models that might otherwise seem counterintuitive. There's something almost eerie about looking up at Venus in the evening sky and knowing that what you're seeing is the brightest possible warning. This is what happens when greenhouse warming runs wild. That beautiful point of light represents a cautionary tale written in sulfuric acid and molten lead, a planetary memorial to climate catastrophe. Ancient peoples saw Venus and thought of love and beauty and divine presence. We see Venus and think of climate physics, of feedback loops and tipping points, of the delicate balance that keeps Earth habitable, and how easily that balance might be disrupted. Both perspectives are valid in their way. Venus is beautiful, even in its horror, but the modern perspective carries an urgency that the ancients couldn't have known. The environmental movement of the 1970s and beyond drew explicitly on Venus research to make the case for taking Earth's climate seriously. Images of Venus's hellish surface, data showing its extreme temperatures, the realization that a planet so similar to Earth in size and composition could end up so radically different, all of this helped crystallize public understanding that planetary climates are not fixed and stable, but dynamic systems that can change in profound and potentially irreversible ways. Some climate scientists have proposed that Venus might have maintained habitable conditions for as long as 2 billion years before the runaway greenhouse took hold. If true, this would mean Venus was potentially habitable for nearly half of its existence, possibly developing life, possibly hosting complex ecosystems, before slowly sliding into permanent desolation. We have no direct evidence for this, but the possibility adds another layer of tragedy to Venus's story. Not just a world that failed to become habitable, but a world that might have succeeded for eons before failing catastrophically. The loss of Venus's water is particularly striking when you consider the chemistry involved. Hydrogen isotope ratios in Venus's current atmosphere, the ratio of deuterium to regular hydrogen, suggest that Venus once had significantly more water, perhaps enough for an ocean 80 meters deep covering the entire planet. Not as deep as Earth's oceans, but substantial. All of that water is gone now, lost to space atom by atom over geological time. This massive loss of water also illustrates another important principle. Atmospheres are not permanent. Without the right conditions to maintain them, magnetic fields to prevent stripping by solar wind, the right temperature range to prevent molecular escape, active cycles to replenish gases lost to space or locked in rocks, atmospheres can change radically over time. Mars lost most of its atmosphere to space, becoming cold and dry. Venus lost its water while accumulating CO2, becoming hot and dry. Earth has maintained a relatively stable atmosphere for billions of years, but that stability required the right combination of factors: our magnetic field, our distance from the Sun, our plate tectonics, our active carbon cycle, possibly even our large moon stabilizing our climate. Venus teaches us that Earth's habitability is not inevitable or permanent, but contingent on maintaining the delicate balance of factors that have kept our climate stable for billions of years. It's a lesson written in planetary scale catastrophe, a warning that comes to us as the brightest star in our evening sky. The goddess of love and beauty became, ironically, the patron saint of climate science, the terrible example that demonstrates what we must avoid, the cautionary tale that reminds us that planets can die, that climates can fail, that habitability is precious and fragile and never to be taken for granted. And perhaps that's the most valuable gift Venus has given us. Not just data about atmospheric physics or greenhouse chemistry, but perspective. A reminder that we live on a world that could, given enough abuse or bad luck, go down a different path. A reminder that the thin shell of breathable air surrounding our planet is not an infinite resource or an indestructible shield, but a delicate system that requires our attention and care. Venus shines in our sky like a warning light, beautiful and terrible, a monument to climate catastrophe that nature herself has constructed for our instruction. Whether we heed that warning remains to be seen. There's a certain absurdity to the question, could life exist on Venus, that you have to appreciate. We're talking about a planet where the surface temperature would melt lead, where the atmospheric pressure would crush a submarine, where the clouds are made of concentrated sulfuric acid. Asking whether life might exist there is a bit like asking whether you might find fish living in a blast furnace. The reasonable answer is no, obviously not. What a ridiculous question. And yet scientists keep asking it, because the universe, as we've repeatedly discovered, has a habit of making the ridiculous turn out to be possible. The key insight is this: Venus's surface is uninhabitable, but Venus is not just its surface. The planet has an atmosphere that extends dozens of kilometers above that hellish ground, And as you rise through that atmosphere, conditions change dramatically. Temperature drops, pressure decreases, and somewhere around 50 to 60 kilometers above the surface, you reach an altitude where the temperature is roughly 20 to 30 degrees Celsius, and the pressure is about 1 Earth atmosphere. In other words, there's a layer of Venus's atmosphere where the conditions are remarkably Earth-like, at least in terms of temperature and pressure. You still couldn't breathe the air, which is mostly carbon dioxide with a healthy dose of sulfuric acid, but the basic physical conditions are far more hospitable than anywhere else on the planet. If life were going to exist on Venus, this would be the place. This region is sometimes called Venus's habitable zone, though that term requires some creative interpretation of habitable. Nothing from Earth could survive there without protection. The sulfuric acid alone would be instantly lethal to any terrestrial organism. But we're not asking whether Earth life could survive on Venus. We're asking whether Venus life, hypothetical organisms adapted to Venus's specific conditions, might exist there. The idea of life in Venus's clouds isn't entirely new. Soviet scientists considered it as early as the 1960s, and Carl Sagan wrote about the possibility in the 1960s and 70s. The concept is that microorganisms might float in the cloud layers, drifting on air currents, absorbing sunlight for energy, and somehow surviving in an environment of sulfuric acid droplets. It sounds preposterous until you remember that Earth has extremophiles, organisms that thrive in conditions we once thought completely incompatible with life. There are bacteria that live in boiling hot springs at temperatures above 100 degrees Celsius. There are microbes that thrive in environments so acidic they would dissolve human flesh. There are organisms living deep in Earth's crust, miles below the surface, metabolizing rocks and minerals in complete darkness. If life can adapt to Earth's most extreme environments, why couldn't it adapt to Venus's clouds? The acid would be a challenge, certainly, but we know of Earth bacteria that can tolerate sulfuric acid concentrations similar to what exists in Venus's clouds. The temperature is actually quite pleasant by extremophile standards, far more moderate than the boiling springs or frozen Antarctic lakes, where Earth's hardy microbes manage to survive. The real challenge would be staying aloft. On Earth, even the smallest microorganisms eventually settle out of the atmosphere. Nothing lives permanently in our clouds, but Venus's clouds are much more stable and long-lasting than Earth's weather systems. The super-rotating atmosphere creates a relatively constant environment at cloud level, and the thick atmosphere means terminal velocity for falling particles is quite low. A small organism with the right shape and density might be able to remain suspended indefinitely, perhaps even actively controlling its altitude by producing or absorbing gases that adjust its buoyancy. For decades, this remained an intriguing but untestable hypothesis. We had no way to sample Venus's clouds directly, no means of detecting whether anything was living in that acid haze. The idea persisted in scientific literature as an interesting thought experiment, occasionally mentioned in astrobiology discussions, but nothing more than speculation. Then, in September 2020, a team of scientists published a paper announcing they had detected phosphine in Venus's atmosphere. And suddenly, the question of Venus life went from theoretical curiosity to front-page news. Phosphine, pH 3, one phosphorus atom bonded to 3 hydrogen atoms, is a particularly intriguing molecule because on Earth it's primarily produced by life. Anaerobic bacteria make phosphine as part of their metabolism. It's also created in industrial processes and can be formed in tiny amounts through certain geological processes. But in Earth's atmosphere, the vast majority of phosphine comes from biological sources. The discovery was made using radio telescopes, the James Clerk Maxwell Telescope in Hawaii and the ALMA array in Chile that detected spectral signatures consistent with phosphine at an altitude of about 53 to 61 kilometers in Venus's atmosphere. The concentration was small, about 20 parts per billion, but significant enough to be measurable and, the researchers argued, difficult to explain through known non-biological chemistry. The announcement created immediate excitement and equally immediate skepticism. This is how science is supposed to work, actually. Extraordinary claims require extraordinary evidence, and the claim that we might have detected signs of life on Venus is about as extraordinary as claims get. Scientists immediately began scrutinizing the data, the analysis methods, the spectral signatures, and the assumptions underlying the detection. Some researchers questioned whether the spectral signature really indicated phosphine or might be explained by other sulfur-containing compounds that could produce similar signals. Others pointed out that Venus's atmospheric chemistry is complex and not fully understood. Maybe there are non-biological ways to produce phosphine that we haven't thought of yet. Still, others suggested that the detection itself might be an artifact of how the data was processed, a signal that looked like phosphine but was actually something else entirely. This is the scientific process at its finest, really. Tentative discovery followed by rigorous scrutiny, followed by more observations, followed by revised interpretations, followed by new hypotheses. As of now, several years after the initial announcement, the status of the phosphine detection remains uncertain. Some follow-up observations have confirmed the presence of something in Venus's atmosphere, producing a signal in the right wavelength range. Others have failed to detect it, or suggested alternative explanations. What we can say is this: there is something happening in Venus's clouds that we don't fully understand. Whether that something involves life remains an open question, one that will require more data, better observations, and probably direct sampling of Venus's atmosphere to answer definitively. The phosphine controversy has reinvigorated interest in Venus astrobiology and sparked serious discussions about how to look for life in such an alien environment. What would Venusian life look like? How would it function? What chemical signatures might it produce? One intriguing proposal is that life in Venus's clouds might exist as a kind of aerial plankton, microscopic organisms suspended in acid droplets, metabolizing sulfur compounds, perhaps using the trace amounts of water vapor in the atmosphere for their biochemistry. These organisms would need to be fundamentally different from Earth life in many ways: different cell membranes that could resist sulfuric acid, different metabolic pathways adapted to Venus's chemistry, perhaps different base molecules than the DNA and RNA Earth life uses. But they might also share some basic features with Earth life. They would need some way to store and transmit genetic information, some method of harvesting energy from their environment, some mechanism for maintaining their structure against the tendency toward disorder. The fundamental challenges of being alive might impose similar solutions, even under radically different conditions. There's also the question of how life could have originated in Venus's clouds, which is perhaps even more puzzling than how it might survive there now. On Earth, the leading theories for life's origin involve shallow pools or deep-sea vents, where complex chemistry could occur in relatively stable environments over long periods. Venus's clouds are constantly in motion, mixing, rising, falling, evaporating, condensing. It's hard to imagine how the delicate chemistry of life's emergence could occur in such a dynamic environment. One possibility is that life originated on Venus's surface billions of years ago when conditions were more hospitable, then retreated to the clouds as the surface became uninhabitable. This would require organisms to adapt from a surface-dwelling lifestyle to permanent aerial existence, a transition that seems almost impossibly difficult, but might be no more unlikely than the transition from sea to land that Earth life accomplished. Another possibility is that life reached Venus from elsewhere, perhaps carried on meteorites from early Earth or Mars, when those planets were experiencing heavy bombardment. This wouldn't answer the question of how life originated, just move the mystery to a different location, but it would explain how Venus could have been seeded with organisms already adapted to survive in extreme conditions. The search for Venus life has also inspired new mission concepts. NASA's Da Vinci Plus mission, currently in development, will send a probe through Venus's atmosphere, analysing its composition as it descends. The European Space Agency's Envision mission will study Venus from orbit using advanced instruments, and more ambitious proposals include aerial platforms, balloon-borne laboratories that could float in Venus's clouds for extended periods, directly sampling the environment where life might exist. These missions face enormous technical challenges. Venus remains one of the most hostile environments in the solar system to explore, but the potential reward, discovering life on another world, even if just microbes floating in acid clouds, would be transformative for our understanding of biology, planetary science, and our place in the universe. There's something beautifully ironic about the possibility of finding life on Venus. For centuries, Venus was imagined as a paradise, a tropical world where life flourished in jungles beneath those mysterious clouds. Then we discovered the reality, hell, not paradise, utterly inimical to life as we know it. And now, after decades of assuming Venus was completely dead, we're circling back to the idea that life might exist there after all, not in the imagined jungles, but floating in acid clouds, where no early science fiction writer would have thought to look. The universe has a sense of humour, it seems. Whether life actually exists on Venus remains unknown. The phosphine detection, controversial as it is, has shifted the question from definitely not to maybe, but we need more data. That's a significant shift in a field where absolute statements are rare and carefully qualified. Maybes are often the best we can do. What we do know is that Venus continues to surprise us, the planet that revealed itself as a hellscape when we expected paradise, that rotates backward when all other planets spin forward, that maintains mysterious UV-absorbing compounds in its clouds despite decades of study. This same planet now presents us with chemical anomalies that might, just possibly, indicate life. Even if Venus's clouds turn out to be sterile, the search itself is valuable. Understanding what chemical processes can occur in such extreme environments, how organic molecules might form and survive in sulfuric acid, what spectral signatures might look like from hypothetical cloud-dwelling life. All of this prepares us for detecting life on other worlds, including exoplanets where conditions might be even stranger than Venus. And if life does exist in Venus's clouds, if those acid droplets harbour organisms that have found a way to thrive in one of the solar system's most hostile environments, that would be among the most profound discoveries in the history of science. It would demonstrate that life is more resilient, more adaptable, more creative than we imagined. It would suggest that the universe might be far more alive than we thought, that life can emerge and persist in places we assumed were completely dead. Venus, beautiful, deadly mysterious Venus, may yet have one more revelation to share with us. The goddess of love and beauty, transformed into a symbol of climate catastrophe, might also become a symbol of life's extraordinary tenacity, its refusal to be confined to comfortable Earth-like conditions. We wait, with our telescopes and our spacecraft and our carefully calibrated skepticism, to see what Venus will tell us next. The veil has been partially lifted, but the clouds still hold secrets, possibly the most profound secret of all, the secret of whether we're alone. So, here we are at the end of our journey to Venus, having travelled from ancient myths to modern mysteries, from Soviet engineering triumphs to the subtle possibility of acid-dwelling microbes. If you're still with me, still listening, still contemplating, perhaps drifting peacefully towards sleep, I'm grateful for your company on this voyage to our most enigmatic neighbour. Venus has been many things to humanity over the millennia. It was Phosphorus and Hesperus to the ancient Greeks, two stars that turned out to be one wandering world. It was Ishtar to the Babylonians, goddess of love and war, both gentle and fierce. It was a calendar marker for the Maya, a cosmic clock precise enough to time ceremonies and guide the seasons. For early science fiction writers, it was paradise imagined, steaming jungles beneath eternal clouds, a younger Earth waiting to be explored. And then we actually looked. We sent our machines there, our emissaries of curiosity, our titanium-clad ambassadors willing to die for knowledge. And what they found was not paradise, but catastrophe, a world that took every assumption about planetary habitability and inverted it, a cautionary tale written in sulfuric acid and molten metal. Yet here's what makes Venus endlessly fascinating. Even after being stripped of its romantic mystery, even after revealing itself as perhaps the most hostile major world in our solar system, it remains beautiful. That evening star hanging in the twilight, that brilliant point of light that has guided travellers and inspired poets for thousands of years, it hasn't dimmed despite what we now know lies beneath those clouds. Perhaps there's a lesson in that. Beauty and terror can coexist. Mystery can persist even after revelation. Venus showed us her surface through radar, revealed her atmospheric chemistry through spectroscopy, transmitted images of her rocky plains through heroic Soviet probes, and yet she still keeps secrets. Those UV-absorbing compounds in the clouds, still not fully identified after decades of study. The mechanism driving super-rotation, still not completely understood. The question of whether anything lives in that acid haze, still genuinely uncertain. We've lifted the veil, or at least pulled it aside enough to glimpse what lies beneath, and what we've found has transformed our understanding of planets, of climate, of the factors that make worlds habitable or condemn them to permanent hostility. Venus taught us that greenhouse effects can run away, that atmospheres can change catastrophically, that planets can die, all lessons we needed to learn about our own fragile world. The goddess of love became our teacher in planetary climate science, which is an unexpected career change if you think about it. But perhaps it's fitting. Love, after all, often involves learning difficult truths, seeing clearly despite initial illusions, caring enough about something to understand it deeply, even when that understanding brings pain. Venus has given us so much knowledge, wrapped in such unexpected packages. The Soviet engineers who designed spacecraft to survive conditions that would destroy submarines, they gave us lessons in persistence and ingenuity that transcend politics and ideology. The radar mappers who revealed Ishtar Terra and Aphrodite Terra, who named every feature for women from across human history and mythology, they gave us a different kind of map, one that honours feminine achievement and presence in ways our other planetary charts generally don't. The scientists studying phosphine signatures and arguing about their interpretation, they're showing us how science actually works, with tentative discoveries and rigorous scrutiny, with uncertainty that's honest rather than weakness. The researchers modelling Venus's runaway greenhouse, they're connecting our beautiful evening star to the most pressing challenge facing human civilization. And through all of this, Venus herself remains. She doesn't care what we think of her, what names we give her features, whether we find signs of life in her clouds or confirm their sterility. She'll continue her slow backward rotation. Her clouds will keep racing around the planet in 4 days, while the surface takes 8 months to complete a single turn. The sulfuric acid rain will keep falling and evaporating before it reaches the ground. The surface will remain hot enough to glow faintly in the darkness, a planet-sized ember burning steadily under its blanket of carbon dioxide. Future missions will visit Venus, Da Vinci Plus descending through the atmosphere, Envision mapping from orbit, perhaps eventually balloons floating in those temperate cloud layers, directly sampling the environment where conditions are least hostile. Each mission will answer some questions and raise others, because that's how exploration works. The veil isn't really lifted once and for all. It's gradually, painstakingly pulled back, revealing layers of complexity we didn't expect. And maybe someday, humans will visit Venus. Not the surface, that will likely remain forever beyond our reach unless we develop technology that seems almost magical by current standards. But the clouds, perhaps. That zone where temperature and pressure are Earth-like, where floating habitats could theoretically survive, where you could step outside in a suit that protects against acid and toxic air, but doesn't need to be a mobile fortress against crushing pressure and melting heat. It's a strange thought, isn't it? Living in the clouds of hell, floating above a surface you could never touch, with Earth just a bright star in Venus's sky. But strange doesn't mean impossible, and humans have always had a talent for making homes in unlikely places. For now, though, Venus remains what it has always been, a presence in our sky, a companion on our journey around the sun, a world close enough to visit but far enough to feel mysterious, similar enough to Earth to make the differences profound, beautiful enough to inspire, and terrible enough to warn. The next time you see Venus hanging in the twilight, whether in the west after sunset or the east before dawn, you might look at it with different eyes than you had before our journey together. That's not just a pretty light in the sky. It's a world, a real place with rocks and dust and strange weather, with a history stretching back billions of years, with secrets still hidden in those clouds. It's also a mirror of sorts, showing us what Earth might have become under slightly different circumstances. What could happen if greenhouse warming spirals beyond control? What the difference between paradise and hell might come down to? Maybe just a bit more distance from the sun, a bit more water remaining in the oceans, a bit more luck in avoiding catastrophic climate feedback loops. Venus is beautiful and deadly, familiar and alien, a companion and a warning. She's the planet that fooled astronomers into thinking she was 2 different stars, that hid her surface from telescopes for centuries, that crushed probe after probe before finally allowing us brief glimpses of her rocky plains. She's the world where days last longer than years, where it rains sulfuric acid that never reaches the ground, where the surface glows with heat even at midnight. And through it all she remains the brightest jewel in our sky after the sun and moon, the evening star that inspired love goddesses across every culture, the morning herald that announces the dawn. Venus contains multitudes, terror and beauty, revelation and mystery, lessons learned and questions still unanswered. As you drift towards sleep tonight, if you're lucky enough to be in that peaceful space between waking and dreaming, you might spare a thought for our veiled neighbour. Not pity exactly, planets don't need our pity, but perhaps appreciation. Appreciation for what Venus has taught us about worlds and climates and the delicate balance that keeps Earth habitable. Appreciation for the persistence of the scientists and engineers who've studied Venus despite its hostility. appreciation for the reminder that the universe is vast and strange and full of places that challenge our assumptions about what's possible. Venus will be there tomorrow night and the night after, and for billions of nights to come. The goddess who became a cautionary tale, the paradise that revealed itself as hell, the world that might, just possibly, still harbour life in the last place we'd think to look. The veil has been lifted, but Venus keeps her final secrets. And perhaps that's how it should be. A little mystery, even in our well-mapped solar system, even in our age of spacecraft and spectroscopy and radar mapping. A reminder that knowing something doesn't mean knowing everything, that revelation often leads to deeper questions, that the universe still has surprises waiting for those patient and curious enough to look. Sweet dreams, fellow travellers. Venus keeps watch in the twilight, as she has for billions of years, waiting patiently for the next visitor, the next question, the next attempt to understand her strange and terrible beauty. Clear skies and gentle starlight, the sleepy astronomer.